So in this video, we're going to be discussing our very first type of workflow, which is the Augmented LLM. The Augmented LLM. Like I said, some might not consider this a workflow. I think even in the standard LangGraph documentation, it is not listed as a workflow. It's discussed, but probably not listed as a workflow. But yeah, I just feel that this is the foundation. This is a solid foundation that you need to grab because it is going to be used in all the different workflows. So yeah, we actually need to spend good time discussing this. Now, what's an augmented LLM? As you all know, LLMs are basically optimized for conversation. They are just conversational tools. They don't have arms and legs. They don't have arms and legs. So they would generate responses, generate images, generate any type of content, but they can't really do anything. And they are stateless. LLMs are stateless, so they don't remember stuff. If you tell an LLM your name, and then in the very next conversation, you ask it for your name, it will not remember your name. It would not. Forget what you've been experiencing in ChatGPT or Gemini or Claude. All those stuffs are augmented. They are all augmented with memory systems, as we're going to be seeing much later in this course. So LLMs basically take in text, predict tokens that simulate the response to whatever you have passed in as a query. To make them do more, like remember stuff and even perform real-world operations, you have to augment them. So any act of enhancing an LLM's capabilities, especially for it to be able to perform real-world operations, is called augmenting. So you augment your LLM with capabilities that will make it function in the real world, because in the real world, we need it to remember stuff, we need it to take actions, and a whole lot more. So in this video, we're going to be discussing the different types of augmentations that you can perform on your LLM. Mainly three of them. We'll then go ahead to practice two of them, and then a dedicated chapter will be left for the third one because it's quite complicated. So yeah, the first one we're going to be looking at is the combo of an LLM and, let me just give you the background so I make it pop. So you have an LLM and tools. LLM and tools, a pair made in heaven. So this is the first type of augmentation that you can perform on your LLM. You can give your LLM tools. This then becomes its hands and its legs. They become its peripherals for it to perform real-world actions. So it can do things like invoke external functions that you've defined in your application, call remote APIs and services, send emails, do all sorts of stuffs that are going to have an impact on the environment or in the World Wide Web at large. So you can give your LLM tools for sending emails, tools for sending Slack messages, tools for making phone calls, different types of tools. You can provide them to your LLM, even tools for retrieve data from Google Drive, retrieve data from Google Docs and stuff like that. You can augment your LLM with tools, and with that, it can interact with its own environment and also with an external environment. And LLMs are smart with this. When they get a request and they see that they have a tool to perform that request, they will invoke that tool. The LLM extracts something called a tool call object. The tool call object is then taken by the runtime. The runtime then calls the tool. So it's not like models natively have the ability to call tools. The LLM is not the one that is going to call your function. It is the runtime. Let me get the lasso tool. So it is the runtime. This box is the runtime. It's the runtime that is going to invoke your tool. So you pass two definitions to your LLM. If your LLM gets a request, let's say I need to send an email with this and that to so person, it then creates something called a function call or a tool call object. So once it gets that tool call object, the tool call object is sent to the runtime. The runtime then looks for the tool that is referenced in the tool call object and calls that tool, which will then go out, do its stuff, return a response back to the runtime for the LLM to decide what to do next. So yeah, that is the first type of augmentation that you can perform on your LLM, tool calling. Now the second one we're going to be looking at is structured outputs. structured outputs. Let's still get our box here. And another one for our LLM. So we still have LLM. It's definitely going to feature in every augmentation. So we have the LLM, and then you can augment it with a schema definition. Augment it with a schema definition to produce a structured output. Let's give these colors. Yeah. So LLM, that should remain green. This would be pink. That's good. Okay, now back to this. So you have your LLM. You can give it a schema to produce something called a structured output. Now, what is structured output? When you are using LLM in the context of a chatbot, it can work in its native language. It just needs to hold a conversation. Free-form text, produces a response in free-form text. That's all good. That's how you want a conversation to go. Nobody wants to talk to anybody and the person is going to, they want the person to respond to them in JSON. Nobody wants that. You want people to respond to you in free-form text. So that's all good for chatbots. But when you're using an LLM within the context of an application, of a program, you will most likely want to pass a defined data format from one component to the other. The LLM also exists as a component within your application. So if you send a request to an LLM and it produces an output and you want that output to go to another component in your program, you most likely want it to go in the form of, let's say, a JSON object, an XML object, or even comma-separated values. You just want it to follow a particular structure. This is where structured outputs come into play. Because in your application, in fact, sometimes models will be operating within different components and sending data to each other. A model is going to be sending data to an email service. A model is going to be sending data to a Slack service, a Twitter service. You have to produce that data in the format that the destination is expecting. So, to implement that, you can simply augment your LLM with a schema. In the Python SDK, you would always use a Pydantic model. So you define a Pydantic model with fields, you use it to augment your LLM, and whenever your LLM decides to respond, is always going to respond with the structure of the schema that you provided. So yeah, that's how you have structured outputs. It makes LLM outputs usable by your applications and other downstream processes. So yeah, that's structured outputs. Now the third one we're going to be looking at is memory. Memory. So we're going to be looking at memory. So once again, we have our LLM in green. Good. And we can augment it with a memory system. So I'm just going to say, what do we call this? Memory system. So that's a memory system. So the third thing you can augment your LLM with is a memory system. And let's give this blue. Yeah, blue is good. So why would we need a memory system? Like I said, LLMs are stateless. They are stateless. When you tell an LLM something, in the next conversational turn, if you try to request that information, it is not going to be available. It's going to tell you, I don't know. You tell an LLM, hi, my name is Fikayo. Hi, my name is John. Hi, my name is Janice. And it tell you, oh, hi, Janice, how are you doing? What can I do for you today? And you're like, what's my name? The next thing is going to tell you that. As an LLM, I have no memory. It is going to tell you that. Like I said, forget whatever you've experienced in forget whatever you're experiencing in ChatGPT right now. There is a memory system behind it. So if you want your LLM to remember stuff, you need to connect it to a memory system. You need to augment it with a memory system. And there are different types of memories, as we're going to be seeing later. There's long-term memory and there's short-term memory. We're going to be seeing that much later. Now, like I said, in this section, we're going to be treating two of these augmentations, and that will be tool calling and structured outputs. These are the two that we're going to be treating. Tool calling and structured outputs. There's a whole section dedicated to memory. It's when you get to that section, you will see why we dedicated a whole section to implementing memory, because we're going to be discussing checkpointers, memory systems, saving stuff to Postgres or Redis and stuff like that. Yeah, so that needs its own section. So we're going to be dealing with memory much later. But for now, we're going to be looking at demos in tool calling and structured outputs. So in this video, we're going to be running our tool augmentation demo. We're going to be augmenting our LLM with two tools. A tool for checking the weather and another tool for calculating a tip at a restaurant. So two different tools performing two different functions. We're going to augment our LLM with these tools. Then we'll run queries through them that we know will invoke these tools so that we can get the expected output. Now, this is a new project file. So let me start by creating a new virtual environment. Since I'm in VS Code, I'm just going to use the VS Code tools and the Python extension to create a new environment. So let's create a new virtual environment running Python 3.11. And with that, I believe when I pull up my command line now, okay, my environment is not activated yet. Let's activate that. Say source venv bin activate. Good. So always make sure you do that so that you can install your packages correctly and we can operate within this virtual environment. So now we need to install three packages. We need to install three packages: LangChain Core, LangGraph, and LangChain OpenAI. Now I'm going to be using OpenAI as my LLM. Feel free to use Gemini, feel free to use Claude or any of the other models. In fact, feel free to use a local model if you know how to set it up. Just go ahead with it. But I'm going to be using OpenAI, and anytime I want to use a different one, I'm definitely going to let you know. So let's get to installing stuff. So pip install LangChain Core, LangGraph, and LangChain OpenAI. That shouldn't take a lot of time, but if it starts taking too much time, I'm just going to pause this video and come back. So yeah, our packages are installed. That's good. You can clear the screen. Now you need to also make sure that you have set the environment key for your LLM provider. I'm using OpenAI, so that'll be OpenAI API key. So just make sure that you've set the appropriate environment for your LLM provider. Else, this is not going to work. So for now, let's close out of this. And I'm going to create a file for this demo, or first a folder for this chapter. That'll be O2 workflows. So yeah, we're in chapter 2 workflows. Then the demo files are going to be according to the number of the video. So if you're looking for the demo for video 0207, just that's the file. That will be the prefix of the file. This is the third video in this chapter, so that will be 0203, and we're going to call it augmented, or rather, no, tool augmentation. Tool augmentation.py. So that's good. Now we have our file. Let us bring in our dependencies. First, let us get LangChain OpenAI in here. Then let us bring in our tools decorator from LangChain Core. Good. Now, most of the time, you can just pass simple Python functions without the tool decorator, but sometimes if you want to annotate it with some extra information, yeah, you should use the tool decorator. Yeah, but for now, let's just have it in, just for the sake of it. The next thing we're going to do, we're going to define our functions. Like I said, we want to augment these with two functions. Your tools are basically functions. They're basically functions. So we want to augment our LLM with two functions. The first one is going to return some dummy data information in JSON. And the other one is going to do some simple calculation to calculate the tip on a bill. So let us get cracking. First, let us define the weather tool. So I'm going to decorate it with tool and say define get weather. It's going to take in a city and return a string. Oh, sorry, I said it was going to return an object. No, it will just return a string. The string is going to contain the description of the weather. So let's get some doc string here. Doc strings are very, very important for tools because they're like prompt engineering for tools. So the more you describe, the more elaborate you describe your tool, the more the model is going to be able to select your tool for the appropriate operations. There are also other best practices like making sure that you name your tool elaborately. Don't do get X or get use stuff, or don't use very vague names. Use clean names that specify an action and a noun, like get weather, get a particular thing. Here I'm just going to add a simple doc string. I'm going to say get the weather for a city. Now I'm just going to construct a weather data dictionary here that will contain the weather information for some hard-coded cities. Now, in a real-world application, you want to call an API. You want to call a weather API. But for now, we just want to see how tool calling works. So we're just going to return the dummy information. So I'll say sunny, 72 degrees Fahrenheit. That will be for New York. For London, we have cloudy, and that will be 15 Fahrenheit. Then lastly, Tokyo will be rainy, 20 degrees Celsius. So we have this dictionary of weather information, and we can simply return the weather for a specific city by saying weather data dot get, pass it the city, and if the city is not available, we'll just say weather data. That's if the user requests data for a city that is not in these hard-coded options. We say the weather data not available. Good. So that's our first tool. It simply returns weather information for a specific city. Now let's define the one that calculates the tip. Call it calculate tip. Give it the bill amount. That'll be a float. Then a percentage, the tip percentage. So tip percentage, which will also be a float. And this should also return a float. Having fat fingers this afternoon. So this should also return a float. Let's go down a little bit. And for this, let us also add a doc string. You don't want your LLMs picking the wrong tool, even though in this case, that should almost be impossible. I don't know a case whereby you want to actually calculate a tip, but the query kind of gets you confused and you calculate the weather or you return the weather. That would be weird. Let's say calculate tip amount based on bill and percentage. So for that, let's just return a rounded figure. Get round correctly. So round bill amount multiplied by tip percentage, which you definitely need to divide by 100. And we want it to return it as a float in 2 decimal places. So yeah, this will be good. Now we have our 2 tools. Calculate tip and get weather. So that's fine. The next thing we need to do is to give these tools to our LLM. We need to bind these tools to our LLM, augment our LLM with tools as we have planned to do. Now to do that, first let us initialize our LLM. Now make sure you are using a model that supports tool calling. Make sure you're using a model that supports tool calling. Very, very important. If your model does not support tool calling, you might run into some issues. I don't know whether LangChain has some sort of ways to bypass or rather create a certain implementation of tool calling even if the model does not support tool calling. But we have better models today, so just use a model that you have confirmed supports tool calling. So we're going to use GPT-4o. And to create our augmented LLM, this is our plain LLM. To create our augmented LLM, we need to bind it to our tools. So we'll say LLM with tools, that's the augmented LLM, will be our LLM. Then we call the bind tools method. Bind tools. Call the bind tool method. And our bind tool method takes a list of tools. So every single tool you want to be available to your LLM, that's what you put into this list. So we have get weather and calculate tip. So this is how you create an LLM that is augmented with tools. You simply call the bind tools function on the LLM and give it a list of your tools. So our LLM is now empowered, is now smarter, or at least it can act now. Now let us test that out. I'm going to create two prompts, one for the weather and another one for the bill. So for the weather, I'll say, what's the weather in Tokyo? What's the weather in Tokyo? For the tip, I'll say calculate a 20% tip on a $50 bill. Okay, so those are our two prompts. And now we can prompt our LLM. We can prompt our LLM that has tools. So first let us pass the weather prompt. So I'm going to say response equals LLM with tools. So we invoke that. We invoke that with our weather prompt. So we invoke that, and any tool call that is returned is going to be returned in a tool calls property. This is where you find any tool calls that is returned. So let's run this first and inspect what we have. Let's run this and inspect what we have before we even get to call the function. So let me pull up my command line. Now we can run Python. Remember I said you should have your credentials for your LLM in place, so don't forget that. Your credentials for your LLM, make sure it's in place. So Python, go to the O2 folder, workflows. Then the only file that is there is the tool augmentation file. Now let us run this. Oh, okay. I just ran it, but I just realized I didn't print the results. So we're basically not going to see anything. We're not going to see anything. It's just going to return. Taking a bit longer. Yeah, so it just returned because I forgot, my bad, to print something out. So let us print the two calls. Two calls. I just wasted tokens there. So let's call this again. And here we have our tool call. We have our tool call object. Now, here is a tool call object. This is how it looks like. We only have one of it because it suggested just one tool. Based on our request, it suggested one tool. The name of the tool is getWeather. The arguments are city Tokyo, which is the only argument that our tool is expecting, which is city. We go here, look at the calculate weather method. You see that it expects city, so city will be Tokyo. And that's a tool call ID, and the type of response is a tool call. So yeah, so that's how a tool call response looks like. Now let us process it and use it to call our function. So we get this. So what I'm going to do in this case, first let us comment this out. What I'm going to do is that I'm just going to loop over the tool calls, and any tool we identify there, you should call it. That's basically what we're going to do. So I'm going to say for tool call, in tool calls, if the tool name, that is if tool call name, as we have seen in the printout that there's a name property. So if the name is getWeather, then we need to call the getWeather function. So we'll say result equals getWeather.invoke. Then we can simply say tool call and args, passing the arguments. So we call invoke, which is coming from this tool decorator on our tool, and we can simply pass it the arguments as a dictionary that can be found in the args property, and it's going to call it. Else, or elif, not L, elif, if the name, so I'm just going to copy this again, if the name is calculate tip, then we'll have to call the calculate tip. Just copy this. Need to call the calculate tip method and invoke it with our tool call arguments. Good. And then we can break out of this loop and print our results. Good. So we're just looping. Definitely we can put an else here. Yeah, let's put an else here. Let's say else. Let's say result equals no tool found. So no tool was found. So yeah, just to undo the other cases where nothing matches with our tools. So now we can pull up our command line once again and run our file. We are currently processing the weather prompt, and as you can see, we queried it for the weather for Tokyo, right? Yeah, what's the weather in Tokyo? And it used our tool, called it, and returned rainy 20 degrees Celsius. Rainy 20 degrees Celsius. Perfect. If we switch that to, let's say, London, and run this again. Oh, sorry. Run this. We get the weather for Long John, which is cloudy 15 degrees Fahrenheit. Now let us test out the tip prompt. Let's pass in the tip prompt and pull up our command line, run our file. Try and do that calculation in your head. Oh yeah, the result already came. I was going to challenge you to do that calculation in your head before it's returned, but it returned. Yeah, 20% of $50 is $10. $10. So yeah, that's how tool augmentation works. So in this video, we're going to be looking at another important LLM augmentation, and that's giving our LLMs the ability to produce structured outputs. Like I said, in your applications, most time when you need to communicate from one component to another, or you want to communicate with an external service, you most likely need an output from your LLM to come in a defined format. That can be JSON, that can be XML, it can even be a comma separated string. You just want it to be in a defined format that is expected by the downstream service that is going to be consuming the output from your LLM. So in this video, let's imagine that you have an e-commerce site, and on your e-commerce site, your users are entering. Let me start creating the file for this demo. So your users are entering reviews. And they will definitely enter the reviews as free-form text. They will enter it in free-form text. But you want to be able to take these reviews, take important information from these reviews, and enter it into some kind of scoring system, some performance scoring system, or just some customer churn analysis system or stuff like that that you have as an internal tool, or just somewhere in your application where your business people can look at it and be able to know what the customer's pulse feels like. So we're going to be creating that in this video. We're going to see how we can extract structured output that we can then pass to a downstream service or another component in our application from the output of our LLM. So let's get started with that. First thing I'm going to do is bring in dependencies, and I will start with the LangChain OpenAI package where we'll import chat OpenAI. Then I will also need a prompt template. So say from LangChain core prompts, we need a chat prompt template. Then, because we're working with structured outputs, like I said, for structured outputs, you need to pass a schema to your model. You need to bind your model's response to a schema. So we need Pydantic. So say from Pydantic, import base model. Like I said, I seem to be having fat fingers this afternoon. So import base model field. Then from typing, let us import a list. We're going to need this in our schema. And let's just import JSON. The JSON package will just be used to print our output. Not like it has any core function it wants to perform in this application. So yeah, so now we have this. And like I said, for a structured output, you need a schema to be binded to your LLM. So let us create that schema. We're going to create a class called product review. It's going to inherit base model from Pydantic. And here we can define the structure that we want our output to come as. So I'm going to say structured product review analysis. No, not Z. Analysis. So as the user sends in their review, the first thing we want to know is the product they're talking about. So say product name of type string, set it to field, and we'll describe it as the name of the product. These descriptions are very, very important so that your model knows the right thing to extract. Then we want to get the customer sentiment, which will also be a string, field, description. I think at this point I'll just copy the description so I can just paste it. So description of this will be overall. There's some quotes there. Overall sentiment. And that will be positive, negative, or neutral. So is the customer happy? Are they angry? Or they just don't really care? So after sentiment, we need a rating. We need the LLM to extract what it thinks the rating is. I want it to be a rating from 1 to 5. So we also want to ensure that it's not going out of that range. So greater than or equal to 1, less than or equal to 5. Next, what are the pros? What are the good stuff we can take out of this review? What are the good things the customer said? That'll be a list of strings. The field. Am I missing something here? Oh yeah, this is not necessary. Yeah, so let's get out. So rating int. Okay, I knew there was something wrong here. Okay. So this also has to be equal to, yeah. So field, the description for the pros is, that will be the list of positive aspects of the review. We also have cons because we like taking criticism. So what are the cons? That will be list of negative aspects. Then we'll like a summary. Yeah, what's the whole gist? Because for some people, for some stakeholders like our board and all that, they just want the highlights. They don't want to get bored by all the details. So description, brief. That'll be a brief summary of the review. So yeah, there's a bunch of typing. Now we have our schema. These are our schema, well defined, and these descriptions help inform the model the type of information that we want to extract from whatever the user has typed in as a review. So let's get our LLM set up. And just as I mentioned when we're doing the tool call augmentation, make sure you're using a model that supports structured outputs. Yeah, make sure. I don't think GPT-4 does. GPT-4o does. It supports structured outputs. But GPT-4, I'm not sure. So be very, very careful the model you're using, else you're going to get an error. So we have our model. Now we need to augment it. How do we augment it? So I'm going to say LLM or structured LLM. That's the LLM we're augmenting. Structured LLM is equal to LLM dot. Now to bind it to our schema, we need to call the with structured output method. With structured output. That is the method that helps us connect our model to our schema so that it can then provide its answers in a structured output or in a structured format. So let us get our schema and put it here. Good. Product review. So anytime this LLM returns a response, it will respond based on this structure. So let us test that out. Let us see how that works. First, let us build a prompt. We're going to build a prompt. Remember, we brought in a chat prompt template. So we're going to build a prompt and say chat prompt template dot from template, not from messages, not from template, from messages. From messages. So here we're going to be adding a system instruction that is going to kind of instruct the model. Yeah, we are taking in a review and we want you to extract it in a structured format. Then the user message is going to pass in the review. So let's start with the system instruction. The system, and we're going to say you are a product review analyzer. A product review analyzer. Extract structured information from reviews. So it's always important to add a system instruction just to further guide the model that this is what we're trying to do. So for the user message, we'll just send in our review text. So that will be the expected input. So review text. That's good. So now we have a prompt and we have a structured LLM. Let's build a chain. So we need to combine these two so that we can then run them together. So for that, we need to build a chain. So I'm just going to say chain. Going to be the prompt. I'll use LCEL to pipe it to our structured LLM. So the input enters the prompt as review text, and the prompt template passes it, and then it gets sent to the structured LLM so we can have our response. So that's good. Now let's pass in a review to this. Now I'm going to be using a review that looks like a real review. So let me just grab that from the exercise files. That's the repo for this course, the GitHub repo for this course, for this file. So you can also get it from there if you're following along. Just grab it. And I'm going to paste it here because I don't want you to see me typing all that. So review copied, paste it. So these are our review text. I bought this wireless mouse last month and it's been mostly great. The battery life is incredible. I've only charged it once in 4 weeks. The ergonomic design fits my hand perfectly and the buttons are responsive. However, the scroll wheel is a bit stiff and makes clicking sounds. Also, it's quite expensive compared to similar models. Overall, I'd give it 4 out of 5 stars. So this is like a typical review you see on Amazon or any other e-commerce store online. So we're going to pass this through our structured LLM and see what it extracts for us. For that, I'm just going to say result equals chain.invoke. Then we'll pass in a dictionary. And the dictionary expects a review text property. And we're going to pass in our review text. Awesome. Now, because this is going to return JSON, we're going to print it using the JSON module. So I'll say JSON dumps results dot model dump, which is a function we get by virtue of using structured output. So model dump, and we just indent by 2. Okay, then by 2. So let's save that. Pull up our command line. Now let us run this file. O2 into workflows, then O204, which is the video name, and then let us see what we get by running our freeform text review through our structured output. Oh, okay, so I didn't set my model correctly. I was thinking it was trying to say GPT-4 doesn't support that. Yeah, so yeah, I needed to say model here. Model, because I didn't name my input, it probably was thinking it's the API key or something. Or I needed to arguments. Oh, take some position argument, but yeah, sorry. Let us run that again. So, where am I? Run file. Make a request, and boom. We have our structured output in JSON. How amazing is that? So product name, wireless mouse. The sentiment says it's positive. Yeah, it was kind of positive. Rating was 4. That was direct. It was just there. Pros, incredible battery life. It mentioned that. Ergonomic design, responsive buttons. Cons were stiff scroll wheel, clicking sound from the scroll wheel. And the customer also mentioned that it was expensive compared to similar models. And the summary that our model gave us is that the wireless mouse performs well with excellent battery life and comfortable ergonomic design. Despite its higher price and minor issues in the scroll wheel, it remains a reliable choice. So that was, yeah, that's kind of like the summary of everything. So yeah, in this video, we've seen how to augment our LLM with a schema to produce a structured output. In this video, we're going to be discussing prompt chaining. Now, things are easier to understand with an example. So let us start with an example. Let's assume that you want to send an email. You want to use an LLM to send an email, or you just want to send an email. Let us look at what that would take. So first, you need to draft the email. Then you need to, for good measure, review the email. You need to review the email. And then, if everything looks good, you want to send the email. Send the email. This was a goal. The goal was to send an email. And what did we just do? We broke it down into steps or subtasks. Draft the email, review the email, send the email. And these are tasks that we will do one after the other. So we will do them sequentially. Yeah, we'll do them sequentially. We'll draft the email. After drafting the email, we send it for review. And then once it looks good, we send the email. This is a typical problem best suited for a prompt chaining workflow. Yeah, a sequence of steps where one step performs a task, passes its result to the next task, and that one also does its job, passes its result to the next task. And it goes on sequentially like that until the final output is achieved. That is prompt chaining. That's prompt chaining. That's how prompt chaining works. It's basically a sequential pipeline of operations and transformations. You have the input going, and you have an output coming out. Simple and straightforward. I think I changed the arrow type at some point. Yeah. So simple and straightforward. You have input, and you have your output after following a series of steps. And each of these guys can be self-contained with a prompt that defines the instruction to be done. If you need to perform some actions, you probably need tools. For example, when you need to send the email, you probably need it. You would need a tool for that. Not probably. You will need a tool for that. Probably like a SendGrid service. You send to the SendGrid API and it sends your tool for you. And you also need an LLM to facilitate all that. So you need an LLM. So let's say this first. Let me put the three of them together first, and so I can copy them together. So let's say this first step, which is drafting the email, you need a prompt. The prompt will take in sender email, instruction, what you want to send the email about. Then using that prompt, the LLM is going to draft an email. Then you send it to reviewing of email. That one would also use a prompt that will give it instructions to evaluate the email by, and probably redraft the email. So it will highlight or identify some issues with the email and refine the email. So it does that. An LLM can do all that. Then finally, you send the email. You probably want to use a prompt to pass instructions also. An LLM is going to do the processing, and a tool is going to send the email. Get rid of these tools. And the tool is going to send the emails. So you have those work components working together in each step, working together to define each step. In LangGraph, that would be a node. These are nodes. Draft email node, review email node, send email node. And with that, you can fire up the process with an input. It goes through the defined processes, and this can be more than 3, it can be 4, it can be 5. It goes through, and at the end of the day, you get an output. That's prompt chaining. That's basically prompt chaining. Prompts and LLMs defining work, the work taking place sequentially, subtasks doing their job, and producing a final result. The output of a particular step becomes the input into the next step, and if there's any error, that particular step can undo it. You can even use retry policies, LangGraph retry policies to undo some of the errors that is taking place in your steps. So that's prompt chaining. So what are the advantages of using this type of workflow? So first, you get to break down complex tasks. You are able to break down complex tasks. No matter how complicated the tasks are, as long as you can break it down, prompt chaining works fine. So you decompose it. You could decompose a large task, complicated problems into small manageable steps. Another thing is that it helps you to improve the accuracy of the entire process. So with each step, you can focus on a single goal, a well-defined task, and you can manage errors within each step. You can also have verification in each step. You can have verification, you can have validation before proceeding to the next step. It also helps to modularize your operations, which is always a good thing. And also, there's transparency because you can view what is going on at each step, and sometimes you can even use different LLMs for each step based on the strengths of the LLMs. For example, to send the email, you don't need a powerful LLM, but to draft the email, you might want to get a thinking LLM. So yeah, those are the advantages. Let us look at use cases. Let me start writing some things on the screen so that you know that I'm still alive here. So let's look at some use cases. First, we have generation and quality control. Processes requiring generation of content and quality control. So for that, you can have different steps. Let's say step 1 generates the initial draft based on requirements that you have specified in your prompt. Then you have another step, which is the second step, that checks for factual accuracy, checks for consistency, tone, and all that. Then you have a third step that takes those recommendations, improves clarity, readability, and all that. Then the final step will format the content for the targeted platform. You can be targeting a blog, you can be targeting email, you can be targeting a social media platform. So the final step can just help you format it to the destination it needs to go to. Another use case is a code review process. So in a code review process, you can also have different steps. For example, step 1 can analyze the code for bugs and errors. Then in step 2, you can check if the code adheres to your style guide and some syntax specifications like that is peculiar to your company. Also, you can have another step after that suggests improvements to the code, and a final step that generates documentation for the code. So these are just some of the use cases where you can use prompt chaining. But in our demo, we're going to be looking at a real life use case where prompt chaining is going to be the star of the show. So in this demo, we're going to be looking at how prompt chaining works. Let me create the file for that. That'll be 0206 prompt chaining. And the demo we're going to be running is going to be a content generation and quality control pipeline. A content generation and quality control pipeline. We get to generate content and we control the quality. So let me just put some string here, or a string here. So our task is to create a content generation pipeline with quality control. Content generation pipeline with quality control. Now we're going to be creating a prompt chain, and this prompt chain is going to take in a topic to write on and our quality requirements. It's going to take in, so let's say input, topic to write on, and quality requirements. And it's going to have 4 steps. The first step, the very first step, is going to generate an initial draft. The second step will fact check the draft. The third step will improve the drafts based on recommendations from the previous step. And the final step will format, or not just a format for publication. Good. So we're going to have 4 steps in our prompt chain. We'll generate an initial draft, fact check the draft, definitely based on the quality requirements, improve the draft based on the recommendations from the fact checking step, and then format the output, the reviewed output, for publication. Let's begin. First, let us bring in our dependencies. So I'm just going to say from LangChain, OpenAI, import chat OpenAI. Let's fix this. Then we also need to get our graph components. So langgraph.graph. Let's import state graph. Start and end. Then because we're going to need state, because we're building a graph, we're getting into the workflows right now. So we're building a graph. So we also need from typing import typedect. Import typedect. So yeah, those are the libraries we're going to need. The next thing we're going to do is create the state for our graph. So class content state. Going to pass in typedect. Typedect seems to be the most efficient way to represent your state in LangGraph. I think the new documentation even specifies something about creating state for, I think, LangChain agents. That's the create agent module in LangChain, and they recommend typedect. But yeah, we're using typedect. So let's continue. So first, we're going to have our topic, which is going to come in as an input. Our requirements is also going to come in as an input. We keep it simple for now as a string. And then we have the draft that we're floating around. We also have the results of our fact check. Results of our fact check. So fact check results, the improved version. Improved version and the final outputs. That's the one that is, or that has been formatted for our destination. So we have our states, keeping it simple with the data types. For now, let's initialize our LLM. Chat OpenAI model equals GPT-4o, which we'll probably be using throughout. So yeah, so we have this in place. Now, the first thing we need to do, or the next thing we need to do, is create our nodes. Each step in the prompt chain is going to be a node. Each step in our prompt chain is going to be a node. And we have 4 steps: the generation step, the fact checking step, the improvement step, and the formatting step. So let us create those. First we create, let me put a comment here and say define nodes. Good. Then here we can say define generate draft, say state, you have type content state, and it will also return the same. Let's have a comment here. Generate initial blog posts draft. And in here, we're going to have a prompt. Multi-line prompt. Or rather, we will use a multi-line string for our prompt. And we're simply going to say, write a 200-word blog post about, then let us pick our topic from the state. So write a 200 blog post about that. Requirements, let me do this. Oh, okay. Requirements. Let's also get that from the state. Requirements. Good. Then we give it some further instruction and say focus on creating engaging, informative content. Yeah. So that's our prompt. That's our prompt. Then we can generate the draft with our LLM. We can use our plain LLM here because we want the draft back as freeform text, so we don't need it structured. So we'll just pass the prompt here and get the content. So that will be our draft. And just so that we can see the flow of things, I'm going to add a print statement here. Just going to say dub. Step 1. Step 1 is for the draft. I'll say draft has been generated. So let us print a part of our draft. Let's say the first 150 characters. Let's tack on the new line there. Let's say, yeah, more to come. So after this, we can simply just return our draft into the state. So just going to say draft. So we update our state by returning our draft back into it. We have our step 1. That's the first step in our prompt chain. Now, I need to get out of this function. Come out of here. Okay. So now we have the first step. The next step is to fact check the draft. So let us write that too. Let's say define fact check. Okay, state means content state and returns content state. This is going to help us check for, or check draft for factual accuracy and consistency. Oh, I need to add more. Yeah. Okay, good. Now, I'm going to speed things up by just bringing the prompt in here. I'm just going to copy the prompt in here, then we can go through it instead of you watching me type the whole thing. So prompt copied. Boom. Now let's go through. Okay, I can put this aside. So this says review the following blog post draft for factual accuracy and consistency. So we get the draft that we've sent from here. And it says identify any factual claims that seem questionable, internal inconsistencies, statements that need citations, and provide a brief report. So that's good enough for us to review. So we're going to say fact check results equals LLM.invoke. As you can see, we're not calling any tools here. We're not augmenting the LLM for now. And even for the fact check results, we don't need a structured output, so we're good. As you can see, our state simply just uses strings throughout. But that doesn't mean that your own use case might not. So we're just trying to keep things simple here. So I'm also going to print the next step. Let me copy that statement from here. Yeah. So yeah. So this will be step 2. I'm going to say fact check complete. Fact check complete, and from the fact check results, we're also going to be displaying the first 150 characters. That's good. Finally, let us return that into state. Fact check results, the same name, fact check results key or channel, and send it into the state channel. So our next step is done. Now to our third step. And what are we doing in our third step? We're taking the recommendations that have been generated or the results of the fact check, and we're using it to, provide a new draft that is more refined. So let us do that. Define improve content state, content state, get that all in here. Keep missing the dash. Okay. So here we want to revise content based on fact check. Based on fact check feedback. Yeah. Feedback. So we're also going to have a prompt here that I'm going to bring in. So prompt copied from the GitHub repo for the course, and boom. So this says here is a blog post draft. So we're giving it our draft again. And here is feedback from fact checking. We give it our fact check results. Revise the blog post to address the feedback while maintaining engaging writing. Keep it around 200 words. So this is going to take the results from our fact checking and improve our document. So we can say improved. llm.invoke prompt, get the content, and then I'm going to get my step print statements once again. It's always good to get feedback while the process is going on, so we see how each node is performing. So this will be step 3 now, and it will be content improved. Content improved, and we'll just keep doing the whole 150 thing. And we can return this. The key is improved content, so let's return it to that state channel. Say improved. Good. Get all that in place. And now we've completed 3 steps. Now we need the 4th step. The 4th step is going to help us format what we have gotten so far to the format for our destination. And you may have guessed, this is a blog post. So we probably need it to come out in something like Markdown or an HTML page. So let's start writing that. We call that define format output. State, content state, to capitalize S. And here, we want to format content, and we're going to be using HTML tags and elements. So we want this to go on a web page. Want it to be a direct web page. We can as well use Markdown and use some of these documentation generators for it, or probably we're preparing the README for a GitHub repo. So for those use cases, you want Markdown. But for this, we want to just output it as standard HTML. So we have a prompt also for this, and I'm going to be bringing it in from the GitHub repo for this course right now. So I'll paste in the prompt, and the prompt says format the following blog post for web publication. This is the improved content. That's what we want to send in, and we want it to add an engaging title wrapped in H1 tags, subheadings where appropriate with H2 tags, paragraphs definitely use the P tag, and we want a meta description, probably in the meta tag of the head tag. Then the output needs to be formatted as HTML because we just want to take the output and push it straight to our website. So we take this, then we say final equals llm.invoke. We pass it our prompt and get the content. Get that content. Then we need to print our step again. So let us go borrow those print statements once again. I'm going to come here. This time, okay, I want to put final. Oh, sorry. Final. This is step 4. And what we're doing here is that we are formatting for publication. So say formatted for publication. So we'll take the final, and this time let's just do 200, just for whimsy. Now we can then return this into state. What's the state key for that? Final draft. So let's return that back into state as the final draft. Final. Good. So we have all our nodes. That is the exhaustive part of this demo. We have our node, and we can start building out our graph. So I'm just going to say builder equals state graph. So here we can just pass in content states. Next, let us add our nodes. Our nodes are going to have the same names as the functions. So to just make things fast, I'm just going to be passing the functions in. So we don't have to define two arguments. So add our nodes. Let me copy this. Let's replicate it 4 times or 3 times. Then this will be fact check, improve content, and format output. So nodes added. Now let us build the flow. This is where we're actually going to build the prompt chaining flow. So this is a very sequential flow. Doesn't have any branching or anything. It's just straightforward. So for that, we're going to say builder.add edge. So we go from the start node all the way to generate our draft. I'm just going to copy this. No, let's just continue. Builder.add edge. So from generating our draft, we then navigate to fact checking. This is our second step. So builder.add edge. From fact checking, we improve the content. Then from improving the content, we format for final output. And once we're done formatting, we can terminate the graph. So that's our flow. That's our prompt chaining flow. Now to call this graph, we need to compile it. So say graph equals builder.compile. We don't need to pass any arguments here. Later on in the state management, or should I say memory section, we're going to see how to pass checkpointers here for persistence. But for now, let's just continue. So we compile our graph, then we can execute it. So I'm just going to say result equals graph.invoke. Then we need 2 inputs. In our state, 2 of them are going to be required inputs. That will be topic and requirements. So let us come down here, say topic. I don't really write about the benefits of morning exercise, which I just started taking seriously. This is the first time I've been consistent over weeks. Yeah, so requirements. For requirements, I'm just going to say target audience should be busy professionals like moi. Yeah, busy professionals like me. And also include practical tips. Yeah, not gym bro stuff. I can't cope with that. So include practical tips, definitely for busy professionals and not people that have time to go to the gym all the time. So yeah, we have that. And now let us print our final results. So print. First, let's have a new line so that we know that our final results appears on a new line that has some space from the other print statements. Let's add some borders. Just going to take this. Then under here, we'll say final result. Let's have that all caps so that it can stand out well. For final result, and then we print another border just to make things look well demarcated. Another border, and then we can say print result. Then from the state, you can get final result, final output. Yeah, that's the name of the channel. So final output from the result. The result contains our end state. So yeah, final output or final draft? Final draft, not final output. Let's do this. Final draft. This final draft. Let me make sure that in our final draft. Yeah, so we need final draft, not final output. Okay. So we have written a lot of code. Now let us run it. We've built a chain with these 4 steps, connected them together with edges for our prompt chaining exercise, where we have our content generation with quality control. So let us run this. Say Python O2 workflows. So we're running O206. And let us hope we are all good without errors. Hit enter. It's going to start printing messages from each step as we have defined. So first we have draft generated. So generated a draft as step 1. Step 2, fact checking. So it's doing some factual claims. We truncated it, so we're not seeing all of it. Then it's improving the content, and boom, we have an HTML output. So final result, we have our HTML output, which it is denoting here with markdown syntax. So we have the head is well formatted. We have the doc type. We have the HTML lang defined. That's the language, English. So we have the head. It gave us the meta description that we wanted. Incorporating morning exercise into your daily routine can enhance productivity and well-being for busy professionals. Learn the benefits and practical tips. And we go down here, it has titled it The Power of Morning Exercise for Busy Professionals. Interesting. So boosting productivity and well-being, the first sub-heading. Increase energy and focus. Those should be benefits, right? Okay, yeah. Then enhancing mood and reducing stress. We have some practical tips here. So for practical implementation, consider quick options like 20-minute jog, yoga, and all that. So yeah, this is concise. This is very, very simple and straightforward. But what we've been able to see here is how to use prompt chaining to take a series of sequential steps that build off each other, and then we can connect them together to achieve a particular goal. So in this video, we're going to be looking at the parallelization workflow. Now, imagine that you want to launch a social media campaign. So you have, let's say the Super Bowl is coming, or the World Cup next year. So FIFA wants to launch a social media campaign. And so they need a post. They want to post that, okay, the World Cup is coming. Let's just say, yeah, the World Cup is coming. They want to post that. They need to post on Twitter. Then they need to generate another post for, let's say, Facebook. Then generate another post for Facebook. Facebook. And they need another post for Instagram, and a final post or another post for LinkedIn. For some reason, the World Cup needs to be held on LinkedIn. So they need to post on these platforms: LinkedIn, Instagram, Facebook, and Twitter. They need to generate posts for these platforms. Now, they can do this concurrently. They can do this simultaneously. They don't need to the Facebook post doesn't have to wait for the Twitter post. Neither does the Twitter post have to wait for the Instagram post or the LinkedIn post. This cannot be done at the same time. Meaning that if we have an input, let's say a topic, we can send it to all these work nodes at the same time for them to generate posts. Yeah, we can. And we can get their outputs and post it to the respective platforms. Or we can get an API, maybe let's say a service like Buffer as an API. So we can say, okay, pipe all that, aggregate all that on the Buffer API or to the Buffer API, and let it send the individual posts. Yeah, we can do that. We can do all this. We can do all this at the same time. I'm just with the lasso tool. We can do all this at the same time. Take our topic, which we're talking about the World Cup, send it to all these work nodes. They will all run at the same time. We can choose to use their output individually or gather it to be processed at one central point. That's how parallelization works. Parallelization allows you to execute LLM operations simultaneously rather than sequentially. So instead of waiting for one task to complete before starting the next, parallel workflows run multiple independent tasks at the same time. They can run multiple independent tasks at the same time or the same task multiple times with different criteria. So yeah, that's how parallelization works. And for this to work, you have to make sure that each task is independent. Each task starts its process and finishes it. So it is not dependent on any other task. So all these tasks, the Twitter content generation, the Facebook post generation, the Instagram post generation, and the LinkedIn as well, they must all be independent. Another use case is when you want to analyze a document based on different criteria. Probably this one is to analyze it based on grammatical correctness. This one is to check tone. This one is supposed to check whether a certain demographic would not be offended by such a post, and maybe another one to check whether it has some sort of, maybe it's like a score, like score it for some on some sort of scale. So you have to make sure that all these tasks are independent. They must all operate independently so that they can run simultaneously without affecting one another. Now, what are the advantages of this type of workflow? First is speed. The very obvious one is speed, because you can generate all these posts at the same time. You don't need to wait. You don't need to wait for Twitter to finish before you do LinkedIn. You can do all these processes at the same time. You can generate all this content at the same time. You can perform all these actions at the same time. And that thing also, it helps, it kind of improves confidence, because you can compare the outputs of these operations to see the quality. You can use different LLMs, so you can actually use different LLMs to actually do the same thing. Let's say for the Twitter, for example, let's say you want to actually just generate for Twitter, but then you generate for Twitter here using OpenAI, you generate for Twitter here using Gemini, you generate for Twitter here using Claude, you generate for Twitter here using Mistral. So you generate for Twitter, you're performing the same task, but with different components, with different LLMs. So you can use it to compare the quality that is produced by each LLM for a Twitter post. Another advantage is that it can help you to perform comprehensive analysis. So you can pick different criteria and analyze a particular input and be able to actually evaluate your content from multiple perspectives all at once. Another advantage is scale. This helps you to easily scale your work by distributing it. So parallelization has powerful features that you can take advantage of. It can help you scale. It can help you generate different results that you can compare. It increases speed, and you can also test out the confidence you have in different outputs for the same task. Now let us look at two use cases where you can employ a parallelization workflow. One is document analysis. Document analysis. You can take a single document. You can use a node to check for keywords. You can use another node to check for formatting errors. You can use a different node to check for factual accuracy. And you can use a fourth node to check for tone, all simultaneously. And you can just give them scores. So let's say you have like a document analyzation tool. You put in a document and it's able to score that document on different criteria independently and all running at the same time. Everything is running at the same time. So you're getting the scores in real time. Another use case is the marketing copy generation that we just discussed. You can generate content for multiple platforms. How amazing is that? In one single go, you can pick a topic and generate content for multiple platforms. So You can basically build a mini social media manager that you can give a topic and it's going to generate for multiple platforms. And you can keep adding platforms, and you can keep removing platforms. Because there's no dependency, it doesn't break the system. You can remove Twitter today, plug in Reddit. You can remove Facebook today, plug in Threads. So everything is all compartmentalized without dependency. And you can swap in and swap out anytime you want. In line graph terms, you create a node that is going to take your input. You can even use the start node. Then you connect this to all the nodes that are going to be running at the same time. You connect them with edges to this same node. Make each node write to a particular shared channel in your state. They can write to a particular shared channel, or you can just have them all connected to this aggregator, which then combines all the outputs from the channels that these nodes write to. Or you can make these nodes write to a list also. You can make them write to a collection, and then this can pick up the collection and process every single item in that collection. But it's easier to see how this works using an example, and we're going to be doing that next. So in this video, we're going to be implementing parallelization using our social media generation example. We're going to be creating a workflow that generates content posts for different social media platforms. Given a topic, is going to generate a post for Instagram, another for Twitter, and one for LinkedIn. Those are going to be our 3 destinations, and all these posts are going to be generated in parallel, that is simultaneously. Then finally, we're going to use an aggregator node to combine all these drafted posts into one output, and each output we're going to put it in a section in the final draft. So let's begin. The first thing we're going to do is import our dependencies. I've already created a file, 0208 parallelization. So let us import our dependencies. Let's get our LangChain OpenAI library. Next, we're going to need our graphing tools. So graph import start, end, and state graph. Then for our state, let us get type detect. Good. Now, the next thing we're going to do is define our states and also set up our LLM. So let us go and do that. I'm going to say class overall state. And what do we need here? First, we need a topic to write about. So take that as a string. Then we need a channel for our Instagram post. Another channel for our Twitter post. LinkedIn also gets a channel. Then we'll create the aggregator node or the aggregator channel where we would have all our outputs gathered and put into sections. So we have this 5 keys or channels in our state. Let's get our LLM ready. Good. Now you may have guessed we're going to be creating one node for every single parallel operation that we're going to be performing. We generate for Instagram, we generate for Twitter, and we generate for LinkedIn. So we need one node for each of them. Now you can have an entry node, but if it is not going to do anything like pre-process the topic, then there's no need for you to have an entry node. You can just start from the start node. So we're not doing any pre-processing to our topic. We're just going to take a raw like that and send it to our parallel workers. So let's just go ahead and start defining nodes for our social media post generating functions. So we'll say define generate Instagram. Take our states. Return the same states. I was forgetting this guy. On the same states. And inside here, we're going to say generate an engaging Instagram post with emojis and hashtags, loved by the Instagram audience. So next, I'm going to add a print statement, and let's make this fun a little bit. Let's add some emojis. For Instagram, I think let's put a camera here. So I'm just going to say Instagram generator creating post. This is more like a progress indicator for our node. So generating post. The next we have our prompt, which is quite elaborate. So to save time, I'm going to copy it from the GitHub repo and bring it in. You can also find it in the GitHub repo for this course. The GitHub repo, in the notes in the introductory section, you can get a link to the GitHub repo from there, and you can copy this stuff to follow along. Or you can write your own. Yeah, you can get creative. But yeah, I'm just going to copy the prompt and paste it in. It says create an Instagram post about, we get a topic. The requirements are engaging and visual language, 2 to 3 short paragraphs, 150 to 200 words max, include relevant emojis, and with 5 to 8 relevant hashtags for the topic that we are going to be passing in. Use a casual, friendly tone because that's the Instagram vibe. Call to action. Yeah, don't forget, there has to be a CTA to engage with the post and make it perfect for Instagram's audience. Yeah. So we have the prompt, and we can say Instagram post. Instagram post is equal to LLM.invoke. Invoke. Pass in our prompt and get the content. So we have our Instagram posts. Let's put another progress indicator here. Might be tedious to put progress indicators, but trust me, it will really help in visualizing the output. So yeah, we're just going to say Instagram generator, say complete. Let's put another emoji here, like a tick sign. Yeah. Good. So we have this, and finally we can return our Instagram post into the state channel. So Instagram post. Perfect. So we have our Instagram post, or our Instagram generation node. The next one we're going to be dealing with is for Twitter. Let's do Twitter. So we do dev generate Twitter state raw state, return overall state, and generate. I don't know. I don't think LangGraph makes use of these doc strings and putting in the functions, but I just like putting them just to help add some description. So, or just comes from good habit creating tools with good doc strings. Yeah. So yeah, let's also have our indicator for Twitter. Can we get the Twitter bed here? Is it possible? Yeah, I still call it Twitter. Call it X all you want, but yeah, still going to call it Twitter. We don't have the Twitter logo here, so we're just going to use something close. Let's say this guy. Okay, so this is going to say Twitter generator creating post, and these indicators will also help us see the parallel operation, because there's going to be race conditions, so it's not like they're going to finish sequentially or in the order that they are defined. They're not going to finish in the order they are defined. The last triggered one might be the first to finish. So they're all going to be triggered at the same time, but it might not be finished in this order. There's Instagram, Twitter, and LinkedIn. The LinkedIn might finish first. So we have this in place. But now we're also going to get the prompt for Twitter. I'm going to bring it in from the GitHub repo, and we're going to continue writing this node. So prompt copied, paste it in here. It says create a Twitter post about our topic, same topic. Requirements maximum of 280 characters, crucial because of Twitter's limits. Punchy and attention grabbing, include 2 to 3 relevant hashtags. Conversational tone, use emojis sparingly, should spark engagement and replies, or replies. Make it perfect for Twitter's fast-paced environment. Yeah, Twitter is always charged up, so you have to be on your toes. Oh, so we have that. So let's say Twitter post equals LLM.invoke prompt. Get the content. Then we can have our indicator to, I think I can just grab that from here. By the way, let me put a new line here. So let's grab this. So that here we can also say Twitter generator complete. So with the start indicators will show us when they are triggered. The end indicators will show us the order in which they are completed. So that'll be fun to watch. Twitter post, so we can return this back to its state channel as a Twitter post. Okay. Twitter post. Good. We're done with the second node. Don't worry, we're very, very close. The third node is going to be for LinkedIn. Almighty LinkedIn. So generate LinkedIn overall state and also return overall state. And there we'll say generate a professional, because everything on LinkedIn is professional. Professional LinkedIn post. Generate a professional LinkedIn post. And to kickstart this, say print. What emoji will be good for LinkedIn? Let's see. Think like a suitcase. Yeah, let's get a suitcase. Or professional. So LinkedIn, we'll say LinkedIn generator, creating posts, Then we need the prompt too, which I'm going to be copying over and pasting in here. So I have that in. It says create a LinkedIn post about our topic, still our topic. Requirements: professional yet engaging tone. 3 to 4 paragraphs, because we like to talk on LinkedIn. Include insights or lessons learned. Use line breaks for readability. Add 3 to 5 professional hashtags. Include a thought-provoking question at the end. Definitely want to generate comments. Focus on value and professional development. Make it perfect for LinkedIn's professional audience. People like us. Yeah, like us that use LinkedIn. So LinkedIn post equals LLM.invoke prompt.content. Then we're going to have that finish print statement again. Put it down here. And going to say LinkedIn. LinkedIn generator complete, and we return this guy into its state channel. Have a LinkedIn post. Okay. LinkedIn, we're done with the 3. We're done with them. Oof. So let us create our parallel workflow. I need to get out of this function. Let's now create our parallel workflow. I was already out actually. So come here. Let's start building our graph. So I'm going to say builder equals state graph overall state. Then we're going to add our nodes. Let's say builder.add node. They're going to be using the same names. So we're just going to pass in the functions. Builder node, then Let's copy this 2 more times. Generate Twitter. Generate LinkedIn. Perfect. So we have our nodes. Now let us build the parallelism. Now, like I said, we are going to start from the start node. We're not doing any preprocessing, so we don't need a node before our 3 worker nodes. So everything starts from the start node. The start node is going to distribute the work to these 3 nodes at the same time. So to do that, you're going to connect an edge between the start node and each of these 3 guys. So say builder.add edge, start, then go to generate Instagram. What's that? Builder.add edge, start, go to generate Twitter. Builder.add edge, start, and go to generate LinkedIn. Yeah, so that's how you perform your parallel operation. If you are not using start, if you're using a node before the parallel operations, this is how you do it. So you just connect from that node to all the worker nodes that you want to send the parallel work to. So we have this, and you can end each of these operations. Probably they are operations that don't return results. They just perform something or cause a change in the environment, and you're okay with them. You can end all of them. You can send all of them to the end node. But we want to aggregate them. We want to gather all of them in a single node. So let us write an aggregator node that is going to aggregate all these operations and compile them into that final report. So let us go up here, just below our LinkedIn node. Let's define an aggregator node. Let's call it aggregate posts. Give it the usuals, overall state, return the overall state. I'm going to tell you to combine all platform posts into a formatted final output. So here we're also going to have a print statement. Just come here, say print aggregator node. What should that? Let's use the clipboard. Yeah, just gathers everything. So we're going to say aggregator, and it's going to say combining all posts. Let's throw in a new line here. Combining all posts. So let us just create a big string that is going to contain all our posts. I'm going to say final output is equals to f string. Then inside here, you can simply build that output. Just going to be a bunch of demarcators for our sections. Say here, give us 70 of those, and the title will be social media content package. Let's copy this, put it under here. Let's have the topic around here. Say topic. Now let's use lowercase letters. Topic, state, topic. Then I'm just going to keep copying this and using it as my title blocks. So for the Instagram, we'll say Instagram post. Instagram post. Then just below it, we'll put our Instagram post. Instagram post. Then, by the way, the aggregator is not going to run until everything is done. The aggregator would run when every of the individual independent nodes are done. That's when the aggregator is going to run. So Instagram post, next is going to be Twitter post. And just below that, we'll have our Twitter post. After that, we're going to have LinkedIn. And below that, we're going to have our LinkedIn post. So that's everything. And we can take this string and just return it to the final output. Final output, final output. Good. So now we have our aggregator node, and to send all our guys to the aggregator node, we'll need to do something similar to this. So here we're going from start to each of the nodes. Now we need to go from each of the nodes to our aggregator node. So from generate Instagram, we need to converge at our aggregator posts node. By the way, we've not added it as a node yet, so let us make sure that we do that, else it won't be recognized as part of our graph. So yeah, aggregate posts. Now I'm just going to copy this and duplicate it 2 more times so that we can take generate Twitter and land it here. Also take generate LinkedIn and land it here. Then finally we can add an edge that will then take our aggregate posts and terminate it at end. Yep, that is everything. That's the construction of our parallel workflow. Now we can compile our graph and run it. So let's say graph equals builder.compile. Builder.compile. Now we have our graph to work with. Let us test it with a topic. Our topic will be the impact of AI in, or rather, on workplace productivity. Let's say we are a productivity influencer. So we want to talk about how AI affects productivity. Yeah, there's like a billion of those kind of content or material online right now. So let's print our topic so that we know the topic that we're working with. Let's step up our emoji game and put a like bullseye. Yeah, so topic. And now we can run our graph. So result is equals to graph dot invoke topic. We give it our topic, and every other thing is just going to be empty. So to speed, I'm just going to copy stuff from here, come down here, and just string up everything. So yeah, string, empty string, empty string, empty string. So all our initial states is going to be empty for each of these guys. Something, okay, yeah, I need to have quotes around all this. Okay, let's do this. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now that I think of it, I probably should have just written this out. So yeah, this is all good. We're passing our topic. Every other thing has an initial state of empty. And we can print our results. So print results. Do we really need to print our results? Did we print final output in our aggregate? Let's see. Did we print final output in our aggregate node? Oh, we didn't. Okay, yeah. So we can print our results. So let's just print our results. Let's do final output. So good. Result, final output. Yeah, that's been a lot. Yeah. And that's the thing with this code. We're going to be coding a lot. A whole lot. So yeah. Let us pull up our command line and say Python O2 folder workflows. And I want to run the 0208 parallelization.py file. Hopefully everything goes fine. Enter. You see, it triggered everything at once. Instagram generator. Then Twitter finished first. Oh yeah, that was fast. But we can still see it. We can still see it. Let's go up. So it triggered everything immediately. Instagram generator, LinkedIn generator, Twitter generator. Twitter finished first, even though it appears here as the third. LinkedIn finished next, then Instagram. And with all that finished, our aggregator combines everything. Social media package, the topic is the impact of AI on workplace productivity. This is our Instagram post, and as you can see, it's using emojis as we instructed it. Emojis all the way. The top text is revolutionizing the workplace with AI, the ultimate productivity boost, and it adds this rocket ship. So adds everything. Imagine a work day, puts a nice rainbow there. And Twitter post, you see, very brief. Twitter, very brief, just uses the rocket emoji, and it says AI is revolutionizing workplace productivity from automating mundane tasks to sparking creativity. Then we have LinkedIn, which is, as you would expect, a bunch of stuff. Just talking and talking and talking. And we have some hashtags here: AI, productivity boost, workplace innovation, professional development, future of work. Let's see. Yeah, Instagram also has some hashtags. Twitter, no hashtag. Yeah. Parallelization. We've been able to generate 3 social media posts targeted for 3 different platforms. So in this video, we're going to be discussing the routing pattern. So let's say you're a top businessman, making a lot of money, living in a very big house. You have a lot of things that you would like to do. You want to make sure that your clothes are dry cleaned. You want to make sure that your flights are booked. You want to make sure that your gardens are trimmed, your dogs are walked. And if you have kids, you want to make sure that you are always booking your nanny to take care of your kids. Now, to do all that, you probably need a personal assistant. And this personal assistant knows all your workers. So they know this guy that takes care of your laundry. They know this guy. They just copy stuff. They know this guy that helps you with your flight bookings. There's also this lady that helps you with your finances. And they also know another lady who is your lawyer. So they know all these guys, all these people that help you get things done. So you have your personal assistant here. Let's say PA. You have your personal assistant. This is your laundry guy here. This is your booking guy here. Your accountant lady here. And your lawyer lady here. So they know all these guys. You don't need to worry about all these guys. They know them. So your function is to give them a task to do. Oh, I want to go to so place, and I'm going to be flying there. So they know that this is a job for the flight booking guy. Yeah, this is a job for the flight booking guy. So they contact the flight booking guy with the details, and he books the flight. Then you ask about your income for the month. They automatically know that it has to go with this person. It has to go to this person. Any legal request has to go to your lawyer. And anything about what you're going to wear the next day and all that has to go to your laundry guy. So they know all this. Your PA is functioning as a router or router, depending on how you pronounce it. Your PA is functioning as a router. And they can go to any of these nodes. Let's make them checked nodes. They can go to any of these nodes based on the task you want them to perform. Based on the task they are given, they can go to any of these guys to perform the operation. They don't get to execute all these guys at once. No, they can execute 2 based on the request. Like, let's say you're traveling. Oh yeah, you need to book a flight and you need to have your clothes dry cleaned. So the laundry guy and the booking guy, they are going to have to do that. So they don't go through all parts. They just go through the part that has to do with the tasks you want them to perform. That is how routing works. It creates this decision tree where different inputs flow through different parts through the system. That's basically how it works. And these are conditional edges. Because they would only be traversed based on the type of task you have asked your PA to perform for you. So based on the task that you give to this node will determine what or where the router is going to send that information to, is going to send that task to. So you have your router here. This is the starting point of your workflow. It analyzes the input and determines which path it should take. Then based on that input, the task, the content type, intent, urgency, topic, category, or whatever criteria, it routes it to any of these guys that are available in your pool of workers. Now, this component is always going to need a structured output because it is going to need a very defined way of knowing what the task is and who to send it to. So this is going to have an LLM that's going to be augmented with structured output so that when it takes the task can be interpreted to any of these guys and it can be able to send the tasks to these guys using a structured output. Then, like I said, these are conditional edges because they will not always be traversed. They will be traversed based on the task that comes in. So they are traversed conditionally. And also, these are specialized nodes. These are specialized nodes. They perform one single task and they are independent. Don't make them depend on each other. They must not depend on each other. They are all independent. And each node contains logic that is tailored to the problem it's supposed to solve. Now, with these guys in place, you can choose to have an optional aggregator. You can always have an aggregator that probably has to take on to the next step because you can actually follow on the process. If you are done with laundry, you can actually just continue to the next node and keep going. So you can have some sort of aggregator or a fallback path for any task that is not included in the pool of tasks. You can have a fallback task. Maybe it will have to route it to another system or to another agent entirely. So that's how routing works. Now, what are the benefits of using the routing pattern? First, it enables specialization. You can have nodes that are specialized for individual tasks. A node to perform this operation, another node to perform that operation, another node to perform that operation. So you can specialize. Another benefit is that it improves efficiency. Why? Because you only have to move through the nodes that concern the task. You only have to move through the nodes that concern the tasks. You don't have to go through any unnecessary part. You move through the part that is concerned with the task that you want to perform. Also, it encourages modularity as your nodes are specialized, just as in the parallelization workflow. And also, you can just break down any type of system into individual specialized workers, and your router is going to perform the work of making the decisions. Your router is going to make the decisions for you. So those are the benefits. Now, what are the use cases where we can use this? What are the cases where we can use this workflow? The example real world scenarios. First is a customer support system. Customer support system. This is awesome for a customer support system because the router can categorize questions into billing, technical support, refunds, general inquiry and stuff. And when it receives a ticket, it will just route to the particular node that is to take care of that particular problem. It will just route to that node. So if it's a billing issue, it's going to route to the billing node. If it's a technical issue, it's going to route to the technical node. And you can create different response templates based on each category. Very fantastic use case. Another use case is document processing. Document processing. Now, oftentimes, you get different types of documents. It can be invoice, can be contract, can be email, and all that. So the extraction and processing logic for each of these type of documents is going to be different. So you can have a router that will recognize the type of document and route it to the appropriate handler. It detects the document. Is it an invoice? Route it to the invoice handler. Is it a contract? Route it to the contract handler. So that specialization and routing logic is just awesome for this particular use case. Another one is a medical triage system. So you have a medical system. It's a medical triage system. And with different categories, emergency, routine checks, urgent, emergency and urgent kind of follow in the same category, or some people that just want to come and make inquiries. So you can route to the appropriate care level based or information resource. You can sometimes you can just send some people to some sort of documentation or some sort of advisor that will advise them on their health. If it's an urgent issue or an emergency, you route them to the emergency section. And if it's a routine check, a regular doctor can take care of that and they can always stay on the queue. So based on whatever issue they come with, you can use this routing logic to manage the whole chaos. So we now understand how routing works. The next thing is to see it in action. In this video, we're going to be designing the customer support system that we described in the concept section. We'll be using the routing workflow to build a customer support workflow that has different categories. One category for billing, one for technical issues, another one for refunds, and one for general issues. Any issues that don't fall into billing, refunds, and technical issues will be sent to general issues. So your router is going to take the user's request or the customer's request and route to the relevant handler. Then each handler is going to process the task given to them and generate an appropriate response for an email that will be sent back to the user that submitted the ticket. If that sounds fun, let's get started. First thing we're going to do is bring in our dependencies. So LangChain OpenAI, import chat OpenAI. Then we bring in our graphing tools from langgraph.graph. Import state graph, start and end. Then from the typing package, we import our typed dict and literal. You'll be seeing why we need literal later. Has something to do with the routes we want to navigate to. Then for our structured output, because as I said, the router has to produce a structured output. So for that we need Pydantic. And from Pydantic, we'll be importing base model and field. So we have our dependencies in. Next thing we need to do is define our state schema. So we're going to say class support state. Then inside here, we're going to have a customer query key to collect our customer query. Then we're going to have a query category channel to determine what category we're going to be routing to. Then response is going to be whichever output is generated by any of the nodes that we routed to handle our request. And then we have tools used. And tools used will just tell us anything that was used to satisfy the request. This is just going to be a dummy list we're going to be populating, and it's just going to be the tools used by the particular handler to handle it. For example, let's say for the technical handler, we can say we access the bug report, we can say we access the log files and stuff like that. So that's just going to help us make it better mirror a real world scenario. So with this state in place, let us get our model set up. So have our model in place. Now the next thing we're going to do is to define the model for our structured output. Just going to put a comment here and say define structured output for classification. By the way, another name for the router is the classifier. It classifies the requests, but everybody just calls it a router. So that defines its general process more. So let's define the structured output for that, the schema for that structured output. I'm going to call it query classification. Pass it the base model. Then inside here, the first thing we want is category. And that's what we're going to set to literal. And to contain all our categories. We have billing. We have technical. We have refund. And we have general. Then another thing we need, just for the model to tell us the confidence level it is working with, to pick the particular handler it has decided to pick as they want to go to. So why are you picking that particular handler. So let us write a description for that. Description equals confidence score, starting from 1 to 10. Or rather, 0 to 1. 0 to 1. So on a scale of 0 to 1, 0 0.5, 0 0.9. Yeah, that makes more sense. So also, what's the reasoning behind what you selected? What's the reason behind selecting that particular handler? Because we need to be sure about all this, or at least know why certain decisions were made. So description, we say why this category was chosen. So yeah, these are the 3 pieces of information that we want the router to return. The category it wants to select to handle the operation, the confidence level of selecting that category, and the reasoning behind it. So we have this in place. Next, we're going to be creating our nodes. Now for the router node, I'm going to call it the classifier or the classify query node. You can choose to call it anything you want, but just giving it a name that kind of describes what it does. You can call it router, you can call it route to handler. Just give it a very descriptive name that describes its function. So here we say state. Oh yes, we already have state. So let's just get the type. Say support state. That's what we'll be returning. And inside here, I'm going to add a print statement. Add a print statement and just say router analyzing customer query. Analyzing customer query. Good. Then we're going to say our classifier LLM. This is where we augment our LLM. We need our LLM to perform a structured output generation. So we can't just use our LLM directly. So we need to augment it. So I'm going to take the LLM and say with structured output, just as we did in the structured output lesson. And then we can pass it our query classification model. Yeah, that's what we're going to do here. So we now have an LLM that can take whatever comes from the user and be able to generate these pieces of data that we're then going to use to make a decision on our conditional edges to route to the appropriate handler. So we have our LLM. Next is the prompt that is going to instruct it. Just as I've been doing so far, I'm going to bring the prompt in, explain it so that we can move on faster. So prompt copied, paste it here. It says classify the following customer support query into one of these categories: billing, questions about invoices, payments, charges, pricing; technical issues, bugs, feature problems, integration issues; refund requests, returns, cancellations; account access, password reset, profile changes, login issues; then general questions, feature queries, information requests, and so on. And we get the customer query from our state. And it says classify accurately based on the primary intent. And as you can see, the categories we gave it are the same categories in the literal definition here for the category field in our structured output. So make sure that that is consistent. So once we have this, we can then invoke the prompt with our classifier LLM. I'm just going to say classification equals classifier LLM dot invoke, and we pass in the prompt. And so that we can see what happened in our classifier, what decision was made, I'm going to add some print statements here. So say the category outputted will be classification dot category. Just going to copy this and duplicate it twice. So we have category. Next is confidence. and that will be confidence, and we just format it to have 2 decimal places. Then finally we have reasoning. That will be classification.reasoning. We have reasoning. So yeah, we can just use this to see what is going on in our router. So put a new line there, and then we can finally return our query category, which is the most important thing in our routing operation, and just simply return this classification.category statement. So yeah, now we have been able to determine our category because that is going to inform the node that we're going to go into. This will be returned here, and we can then use our conditional edge to check and route. So we have this in place. Let's, with that, I think I need, okay, I'm out of the function. So yeah, we have that router defined. The next thing we need to define is the billing. What is going to handle the billing for us? So for that, first I'm going to say print. Oh, sorry, I think I didn't define. Sorry, I was way ahead of myself there. Okay, so we need to define a node for our billing operation. Say define handle billing. It's going to be our billing node. Say state, support state, then inside here we're going to add a print statement so that we can know that we're in our billing operator, because if anything has to do with billing, we have to know that we're routed to the billing node, and it will display to make us know that the billing handler is currently handling the request. So it's a billing handler, so processing billing query. So once we have this in place, we then need our prompt and LLM. A simple LLM is going to do this operation. We don't need to augment it with anything. But first, let us get our prompt. So prompt pasted, and here it says you are a billing specialist. Handle this customer query. We get the customer query from state, and it says provide a helpful response that references billing policies and procedures, offers to check the account details, provides clear next steps, and mentions relevant payment options. And says keep it professional and reassuring, because this is money issues. So yeah, you need to really keep it assuring or reassuring. So once we have our prompt, we can say response equals, then use our LLM. Like I said, we don't need to augment our LLM. We just need to generate content and freeform content. So I'm going to pass in our prompt to that. Say content. Then we can return back into our state object. Say response. For response, we can just return our response here. Then for tools used, we'll just assume some tools. So let's say we used our billing database and our payment processor. So we also kind of queried our payment processor to know that, or to inquire from them about this particular transaction that the customer is worried about. So yeah, that's our first handler, our billing handler. So I have that in place. The next handler is for technical issues. I'm going to just copy this top section so that I don't have to type it over and over again. Just copy it and edit it. So this will be handle technical. Handle technical, and this will be the technical handler. Then let's just replace this with something technical, like let's say spanner. Okay. Or techie. Ooh, that's kind of jumped here. Okay, so we have our technical handler. And the next thing we need to do is also get our prompt, and our prompt is going to contain the instruction for handling the technical issue. Then we pass it to our LLM. Also, this LLM does not need to be augmented, so we can just use our plain LLM, because all we want to do is generate a response email. So I'm going to grab the prompt and paste it here. Then we're going to say response equals llm.invoke. Pass on the prompt, get the content, and then down here we can say technical handler response generated. Did we have that in the billing stuff? Oh yeah. So we need to know that it's done. So here I'm just going to put the one for the billing handler. So like I said, this helps us a lot to know how the process is flowing. So here I'm just going to say billing handler, so response generated. So in the same vein, I'm going to come down here, do that for the technical handler, and then we can simply just return stuff back into state. Response will be response, and tools used. Let's make up some tools. So let's say we interacted with the knowledge base. Definitely for technical issues, that is necessary. Then we also use the bug tracker. Then we definitely queried our system logs. So those are the tools that we used. So that's good. Now I'm going to be doing one more thing to further speed things up. So let us copy this entire handler so that we just get to replace the name, the prompt, and just a couple of things. So the next one is going to be our refund handler. So I'm going to say undo refund. Undo refund. This will be a refund. Let's put a money bag here. Money bag, money bag, money bag, money bag. So money bag, yeah. So undo refund, here too we put refund. So yeah. So we just have that for our refund. This will be refund too. Refund query. Let me make sure that I've done that for technical. Okay, I haven't. So technical handler. Okay. So everything here changed to refund, refund, refund. Then we need to get I'm going to switch this prompt. I need to switch this prompt to a refund prompt. So let us do that. So for refund, I'm just going to switch this prompt from the technical to the refund prompt. And it says you are a refund specialist, handle this customer query. This is a customer query. Provide a helpful response that explains the refund policy clearly, outlines the refund process and timeline, asks for necessary information, order number, reason, etc. Shows empathy and understanding. Be empathetic and solution focused. So we do that. We generate our response. We say that it's generated. Then tools used. We queried the order database and also checked our refund processor, which is a subset of our payment processor. So our refund processor, we check that. That might actually be an agent. Cool name for an agent. Refund processor. So yeah, we have that. And for general issues, I'm just going to bring the handler in and explain. So to save some time, I'm going to paste that in. Very similar structure, but for you, it might not be this similar. So you want to make sure that you are making sure that each handler is tailored to its function. So undo general issues, undo general handler processing query. You see with the information icon, just general stuff. You are a general support specialist, undo this customer query. Take our customer query, and it says provide a helpful response that answers their question clearly, provides relevant links or resources, offers additional help if needed, suggest related features they might find useful, and make sure that you're friendly and informative. So give a lot of details. Then we generate the response. We say that it's generated, and we contacted the knowledge base and the FAQ database because it's an information heavy request. So we have our handlers in place. We have all our handlers in place. And the next thing we need to do is how are we going to route from this router, our classifier query node and our router node, to these guys, to these four guys, based on the request coming from the user. And like I said, we need to create a conditional edge. We need to create a conditional edge. So we're going to be writing a conditional edge function that can return any of the categories based on the query category. Good thing we've named the categories with exact names, and we can always return that with the query category because those are the names we are also saving into the query category from the classifier router. For the classifier router, those are the same names that we are using across board for each of the categories. So let's define our function that will route our query. This is actually the function that is performing the routing work. This is the function that is performing the routing work. Sometimes you can do your routing directly in the router node. And do directly with router node with something like command. You can use the command API to do that. But let's just be more explicit and dedicate that to a separate function. So this function is going to take in the state, which is going to be of type support state, and it's going to return a literal. A literal, which can be of different types. So the literal can be of any of our types, which is billing. It can be technical. I'm just hope I'm writing those correctly. Then we have refund. We have refund, and finally we have general. So those are the literal strings you can return. And here we're just going to print to show that our routing operation is going on. So I'm going to put an F string here. Have a part emoji. Oh, let's say route. Yeah, so something like this, and here we're going to say routing. So know that the routing is going on. Directing to state query category. Directing to state query category handler. Put a new line there so that we can know that the routing is going on. And here all we need to do is return the state query category. Because we have already told our structured output to use these names. So it's just going to return any of those names. It's going to return any of those names in the query category. And that's what we're going to use to route to our handler node. So we have this here. We can start building the graph. So builder equals state graph support state. Then we add our nodes. This time we're going to be adding our nodes with specific names. We're going to be adding them with the names of our categories. Yeah. For classifier query, that's fine. We're just going to give it the same name as the node function. Then for others, say builder.add node. The first one we're going to be adding is billing. And billing is going to be handled by undo billing. Let me copy this. Next, we're going to be handling technical. And that is going to be handled by the undo technical function. Oh, I should have copied this a bunch of times. So, yeah. So, we have refund next. Is it refund or refunds? Let's make sure. Refund. Yeah. And the classifier is refund, okay? singular, not plural. So refund is going to be handled by handle refund, and technical, or rather general, is going to be handled by handle general. General, handle general. Perfect. So now we can start building the structure of our graph using edges. The first one we're going to do is to get started from start to classify query. Classify query node. So we have that. Now we need to move conditionally, because from classify query we need to route. So we're going to say builder dot add conditional edges, and we'll say we want to go from classifier query. Then next is the function that is going to return where we want to go to, which is route query. And then we're going to give it a map of locations to go based on its return value. So if you return billing, go to the billing node. If you returned technical, just going to be copying at this point. If you return technical, go to the technical node. If you returned refund, go to the refund node. And finally, if you return general, please navigate to the general node. So that's good, but we need to terminate these guys. So we need to take all our nodes and make sure that they are terminated. Or you can route to the next thing. You can route to the next thing. You can route to another node that just takes over the process, probably a node that will send the email, because here we're not sending the email, we're just generating the emails for these categories. But from these categories, instead of going to end as we will be doing now, you can actually go to the node that is going to use a tool to send the email itself. So say end, billing end, and let's just copy that a bunch of times. Billing end, technical end, refund end, general end. Good. Awesome. So now we can compile our graph for use. So graph equals builder dot compile. Builder dot compile. So we have that in place. And I'm going to bring in a bunch of prompts for different use cases so that we can test them out. One for billing, one for technical, one for refund, and one that is just going to be general. So let's paste those in. Our example prompts, we have a billing prompt, a technical prompt, a refund prompt, and a general prompt. The billing prompt says, I was charged twice for my subscription this month. Can you help? But let's just test them one by one, and from there we will be explaining what the prompt is saying. Let's say result equals graph dot invoke customer query is going to be our prompt. For now, let us give it billing. Query category empty. Response empty. And tools used empty. Then we can come down here and print our final response. If we print, have some demarcation there, let's say 70. And down here we can say print final response for restate, no. Final response for result, query category. So we know the category that this response is for, query category. Let's make it uppercase so that can just flow with this screaming header. So we have that. Just paste this down here. Do we need this F? We don't need it here. Get this down here. Then we can print the response. So result, response. That's the email that is going to be going out to the user. And just so that our tools used section is not going to be wasted, let us print out a more detailed report by talking about the tools used. Let's get another spanner here. Let's say spanner. Tools used here will then be, let's create a join statement that is going to concatenate all our tools and make with a comma, comma separated. So it's a join results tools used. So we have all this in place, and we can run our code now. A lot has been done. We created our router. We give it a structured output, and the LLM that processes the request is using a structured output, or rather is augmented to produce a structured output so that it can give us the exact query category to navigate to. Then we create the handlers. We have our routing logic here, and we added our conditional edge to route to our nodes. So now we're giving it a billing query, and let us see what it will do with it. You can say Python O2 workflows O210 routing.py. Let's hope everything goes well because we did a whole lot of typing. Hit enter. So analyzing customer query is a billing request. So routing to billing handler, billing, processing the query, and boom, done. Let's take it from the top. Where did we run? Okay, we ran it here. So the router says it's analyzing the customer query. It then gave us the analysis result. The category is billing, confidence is 0.95, really high. Reason is because the query specifically mentions a billing issue that is being charged twice related to a subscription. The customer's primary concern is about incorrect charges, which falls under the billing category. And that is based on the prompt that we gave the classifier. We instructed it on issues that fall under billing. Then it says routing to billing handler. Then the billing handler is processing the query, is generating it, and then we get our final response, which is the email. The subject is assistance with duplicate subscription charge. This is where the customer name goes. This is something we can always feed in dynamically from a long-term memory. Say thank you for reaching out to us regarding your billing concern. I apologize for any inconvenience, blah, 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 standard stuff. And says, please let me know if you'd like to proceed. I'm here to assist you with any further questions or concerns you might have. Warm regards. Then you put the full name, your position, that's the person handling the request, which you can also query from long-term memory, from Postgres or any database that is used, and then put in your company information and the information of your staff that is handling this request here. And says for tools used, we use the billing processor and the customer and the payment processor. That's the billing request. Neat and clean. Let's try a technical issue. So technical. This is the app keeps crashing when I try to upload files larger than 10 MB. So let's replace this with a technical prompt. Pull up the command line once again and run this. So analyzing the query is technical, high confidence. It's going to the technical handler, drafting the email, and very soon we should have the output. And boom. Now we'll see this. It's kind of formatted in Markdown, I guess because it needs more structure. It says, I'm sorry to hear you're experiencing issues with the app crashing when uploading larger files. Let's walk through this together to identify the problem and find a solution. Here are some troubleshooting steps you can follow. So it says update the app, check internet connection, clear the cache. Then if it's iOS, do this. Device storage, test with different files. If it's Android, it has some specifications too for Android. Then try to ask some clarifying questions in case you still couldn't fix all this. So if you can answer these questions, probably there will be context for providing a better solution. Then also it suggests a workaround. If the issue persists, consider breaking your files into smaller chunks below 10 MB if possible. This can help mitigate the problem while we work to identify a permanent solution. So you see, this is real life. This is something that you can deploy behind the fast API endpoint, and it will serve as your customer service responder. But you need to really ground it in your context. You can't just use it like this. You have to ground it in your context. We have a whole section on persistence and memory, so all that you can understand how to ground your systems in your own private knowledge, in your domain knowledge, so that it can answer questions based on the service that you are rendering. So yeah, we've tested technical. Feel free to test others, test refund, test general, and tell me what you found out. Tell me what you found out. But I must confess, even though this was quite long, that's been quite fun. So in this video, we're going to be looking at another workflow in LangGraph, and that is the Orchestrator-Worker Workflow. So imagine that you have a PDF file. You have a PDF file, and your PDF file has multiple pages. So let's say it's a book. So you have a PDF file. Let me make this without a background. And your PDF file has multiple pages. So there's another page here and another page. You get the gist. So your PDF file has multiple pages. Now you want to summarize the entire book. So this is a book. This is an entire book. Let's call it book with numerous pages. And you want to summarize all the pages in this PDF file, this book. Now, you want to delegate that to nodes that can summarize, but you're going to be giving each node different pages. This book has different pages, page 1, page 2, page 3, page 4, up to page N, and you want to give that to individual nodes. You want to break it down into pages because you want to summarize the entire book. You break the book down into pages, and you want to summarize the entire book. Or you want to even summarize it chapter by chapter. Summarize chapter 1, summarize chapter 2, summarize chapter 3. And you know that you have to pass this to summarization nodes. So this node gets one chapter. Let's just go by chapters now. This node gets one chapter. Another node gets another chapter. And a third node gets the third chapter. And the end node gets the end chapter. Let's make this dashed now. And yeah, gets the end chapter. So you're going to be giving each of these nodes different information. In this case, chapters. You're going to be giving them different chapters to process. And you don't know, you want this workflow to work for any type of book. And books have different number of chapters. There's no fixed amount of chapters every book in the world must have. So you have some books that have 5 chapters, some books have 10 chapters, some books have 13 chapters. So you have to be able to dynamically spin up these nodes and pass them different states, that is different information. And each node is going to summarize its chapters. And at the end of the day, you're going to gather everything. From node 1 to node N into a single document. You're going to gather everything into a single document that will then be your final summary. Let's give these different colors. Maybe it's going to like improve the visualization. Let's see. This blue. Yeah, that works. Yellow. Yeah. So at the end of the day, you pass all your chapters into nodes, into summarization nodes, and each summarization node is going to summarize each chapter, and at the end of the day, they're going to aggregate and synthesize everything into this final summary. Let's call it final summary. Good. Yeah. So this is basically how the orchestrator worker workflow runs. This is how it runs. You have a complex task. You want to break it down into subtasks, and you want nodes to work on each task. And when they finish working on each task, they can bring everything together and give you the final output, the final result. More like a map reduce process, like we saw in the send lesson for performing MapReduce, and we're going to be seeing send in this operation also, because send is what LangGraph basically uses to execute this workflow. But basically, this is how the Orchestrator-Worker Workflow works. You use a central orchestrator to break down a complex task into smaller tasks. Then you dynamically create nodes, and to each node you delegate a subtask. You delegate a subtask to each node, and those nodes are called workers. These nodes are called workers. And this is your orchestrator. This is your orchestrator. So your orchestrator gets to break down the book into chapters, and those chapters become the subtasks. It then passes it to these worker nodes, which are the summarizers. They're the summarization nodes, and they perform their summaries on each chapter and aggregate everything into a final summary. So once the workers are done, the workflow synthesizes the workers' outputs into a final result. The orchestrator is the one that manages the overall workflow, while the workers just focus on their specific tasks. They focus on solving the pieces that have been given to them. That's basically how the Orchestrator-Worker Workflow works. Now, let us look at the advantages of using this workflow. First, it helps you to handle dynamic complexity. Just write that down so that you'll see something on the screen. Yeah, so it helps to handle dynamic complexity because you can simply break down tasks to the number of subtasks. You don't need to know the number of subtasks in advance. You can simply take a complex task, break it down into subtasks, and you don't need to know the number of subtasks in advance. So you can dynamically handle complexity. Another thing is that it enables you to perform parallel processing. Parallel processing. So you're able to perform parallel processing in that you can take each subtask and operate on them independently, and all the subtasks get to run simultaneously. Each worker performs his work independently and all the workers are running simultaneously. So parallel processing, just like in our parallel workflow, but this time you are doing it dynamically, but also running operations in parallel. Also, you have coordination. Because the orchestrator node, let's write that here, coordination. The orchestrator node gets to coordinate the entire activities of the worker nodes and also collect their results and decide what to do with their results. So the orchestrator helps you to manage the breaking down of the task. There can be different criteria with which you want to break down the complex task into subtasks. So the orchestrator helps you to manage that, and it also helps you to synthesize the results. That is one other advantage. Another thing is that you can scale dynamically. Let's have that on the board too. You can also scale dynamically. Yeah, good. No, that's why. That's better, dynamically. Okay. So you can scale dynamically in that you can create as many workers as necessary for the task. Yeah, you dynamically spin them up. They are spun up on the fly. So you can easily scale your operation dynamically. It also provides for separation of concerns because the orchestrator manages the breaking down of tasks, manages the synthesis, while the workers just focus on handling what has been given to them. So with this workflow, you can have separation of concerns. That's also one of the advantages of using this workflow. The orchestrator is responsible for breaking down the tasks, while the workers simply focus on what they are to handle. So yeah, those are the advantages of using this type of workflow, and it also kind of informs when to use this type of workflow. But let us look at some use cases. One is code refactoring across multiple files. So here you can have your orchestrator identify which files need updates. You create a worker for each file to refactor, and then you can synthesize all the changes, ensuring that you have consistency across your code base. So code refactoring is one of the use cases. You can also use it to manage large data sets. You can use it to analyze large data sets. An orchestrator can help you split a large data set into chunks. Then you can create workers, and each worker is going to analyze each chunk. Then you can aggregate statistics and insights from all the results produced by the workers. Another use case is distributed testing. So in distributed testing, you can use your orchestrator to identify different test cases to run. Then you create workers for each test suite. create workers for each test suite, and at the end of the day, you can aggregate all your test results into a final test report. You can aggregate all your test results into a final test report. So yeah, that's the Orchestrator-Worker Workflow. We've looked at the advantages of using this workflow. We've also looked at use cases where this workflow can be applied. And now let us see how we can use it in code. So in this video, we're going to be running a demo to showcase our Orchestrator-Worker Workflow. We're going to be creating a research report generator. This research report generator will be given a topic. Then an orchestrator node is going to take that topic and break it down into subtopics or aspects to research on. We'll then spin up workers to research on each aspect that has been given each subtopic. And then once the workers are done, the results are collated and synthesized into a full final report. So that is our demo. I'm going to be creating a new file for that, and that will be the O212. I will call this Orchestrator -worker workflow, or just orchestrator-worker.py is okay. Orchestrator-worker.py, and let us get started with our project. Now, the first thing we're going to do is to bring in our chat model. We want an LLM to power this, so we want to bring in a chat model. Let us bring in our OpenAI library. You can use any LLM you want, as long as you get the LangChain implementation right. But for this, we're going to be sticking with OpenAI. So let's import chat OpenAI. Then let us bring in our graphing tools. Here we'll get state graph, start and end. Then we're going to need send. So from langgraph.types, we're going to need the send API. So bring in send. That's what we're going to be using to dynamically assign work to nodes. Then we're also going to bring in some classes from the typing library. That will be typedect, list, and annotated. Then we want to aggregate our results into a particular state channel, and to do that, I'm going to be bringing in the add method from operator. Then for our models, just going to bring in Pydantic. We import base model and field. We're going to be using this to define some of the structured outputs that we're going to need along the way, because the orchestrator is going to need to produce structured outputs, so this would help. Now let's begin writing our main application, starting by defining our overall state. Now we're going to be defining two types of states for this demo. We're going to be defining an overall state that will be for the entire graph. Then for each worker node, each of them would operate in a private state. Each worker node is going to operate in a private state. So we're also going to be defining a private state schema for each worker node. So let us define our overall state first. I'm going to say class overall state, pass that typedect. And the first channel we're going to create is for the topic we want to research. So research topic, and let's just set that to a string. A string. Next is sources. I'm going to call this sources, but it's just the breakdown of the topic into different subtopics. So it's a string, and the next thing is going to be worker findings. So our worker is going to be investigating each source and research for us and return some findings. This will be annotated, be a list of dictionaries, because each worker finding is going to be sent back as a dictionary. And for the reducer, we're just going to input the add reducer. So what we're trying to say here is that we'll take this research topic. Our orchestrator is going to break it down into different research headings. We'll call them sources. Then our workers are going to research these sources, and whatever they find is going to be collated here. That's why it is a list. They're going to be returning dictionaries. That's from their research. The workers are going to be returning dictionaries. So this is going to be a list of dictionaries. And because we're going to be gathering them here, we need a state reducer that is going to help us append each worker's research finding into this worker findings channel. So that's good. And in our aggregator node, we're going to have a final report that we're going to generate that will be set to a string. Yeah. So that's good. That's for our overall state. Next, we need to define the private state that our workers are going to operate with. I'm going to call that worker state. Feel free to call it any name you want that is descriptive for the purpose in your application. But in this demo, we're just going to call it worker state. Now for here, each worker is going to be taking a source. That is one of the sources in this list. And we're going to have a worker ID just to uniquely identify our workers. That will be an int. And going to say research topic. Let's give it a research topic, just so that he has that in context. So yeah, that's good. The next thing we need to do is create the output of the orchestrator. Now, as I mentioned earlier, the orchestrator needs to provide or produce a structured output, because that's how we can then pass information to our worker nodes. We can't pass information to our worker nodes from raw LLM text. We have to get a defined data structure that we can then distribute to our worker nodes. And like I said, what our orchestrator is going to be doing is taking this research topic and breaking it down into sources. So that means we want to get some sources back. So I'll just create a new class and say research plan, a base model. And here the first thing we're going to define is our sources. This is going to be a list of strings. And we're going to define it as a field, as a pedantic field. For the description, we'll say list of specific research sources or aspects to investigate. And we want to restrict how many of that the LLM suggests. So we'll give it a max length of 5. So don't suggest more than 5 sources. We don't want to just keep going on and on and on and on. Then the next thing we will define is a helpful class property called reasoning. And what reasoning would do is just to make the LLM give us the thinking behind choosing the sources it has decided to choose. So we'll say brief explanation of why these sources were chosen. Yeah, so we don't just want it to just return sources without context. So we want it to tell us why these sources were chosen. So that's good. We have our state schemas defined, and we also have our structured output schema defined. The next thing we're going to do is set up our LLM. So let us instantiate that. Say LLM equals chat OpenAI. I want to use the GPT-4o model. So good, we have our LLM defined. Now we need to create our nodes. And we're going to need 3 nodes. The first node is going to be the orchestrator node, which is going to take our topic and slice and dice it into different sources or different talking points. Then we're going to create an instance of our worker node. That's the worker node that is going to be duplicated, but given different parts of the breakdown that the orchestrator has done so that it can work on them. Each worker node that spins up can work on each part or each source that the orchestrator node returns. And then we'll have our synthesizer node. This is the one that will collect all the findings from our worker nodes and prepare a final report from that. So let us start with our orchestrator node. So say orchestrator, and I'm going to call that function plan research. Plan research. It's going to take in a state of the type overall state, and it's going to return overall state. Now you know I like print statements, so we're going to print something here. I'm just going to print, let's put a new line here first, and add that to 70 dashes. Good. And under that, I'm also going to print 70 dashes, just as the divider for the title I want to put here. And in between that, I'm going to say print, and here we'll say orchestrator. Let me see if I can put a robot emoji there. Yeah, I'm the emoji guy. So this is the orchestrator, and here we're going to label this as orchestrator and say planning research strategy. Planning research strategy. So that's good. Let's print our topic. Here we'll say topic is, and we can get that from the state. Our topic is research topic. And let's just stick a new line character there. So yeah, here we'll be able to know that our orchestrator is running. It's always good to add all these labels, especially when we're running examples, so that we can see where a particular action is taking place. So let us get to planning. First, we need to augment our LLM. So I'm going to say planner LLM equals LLM dot with structured output. Then we can pass in our research plan schema. Give it to this. Good. And then we can then write our prompt. So we need to produce a structured output, like I said, from our orchestrator, so that we can get a data structure that allows us to distribute to worker nodes. That's why we're creating our planner LLM, which we have augmented with our research plan schema. So now let us get our prompt. The prompt is a bit lengthy, so I'm going to bring it in and explain. But you can find it in the project files, in the GitHub repo for this course. You can find it there, and you can play around with it. So I'll just paste the prompt here. It's good. Now this prompt says you are a research strategist planning a comprehensive investigation. The research topic is this, which we are getting from state. Critical instruction: generate between 3 to 5 specific research sources or aspects to investigate. Do not generate more than 5 sources. Each source should be specific and focused on a distinct aspect, relevant to the overall topic, complementary to other sources, minimal overlap. We don't want duplicating sections or being repetitive. Then concrete enough to guide targeted research. Examples of good sources. It's always good to do this with your prompts. Short them with some examples. So clinical trial results and efficacy data, economic impact, and blah, blah, blah. Just give it a bunch of topics so that it knows how to craft its top talking points. It knows how to craft them the way you would like. Then generate sources that will provide comprehensive coverage of the topic. This is also a very, very important instruction to give to the model so that it doesn't just generate things that are not coherent or doesn't have the proper cadence. And also you want it to generate them in such a way that it covers the topic from a starting point to a sufficient ending point. So yeah, that is our prompt. Now let us generate our research plan. And here we're going to take our planner LLM and invoke it with our prompt. That's good. Now to observe the output, let us see what it is able to give us. I'm going to say print, use F string there, and say orchestrator generated. Then let's get the length of what we got back from our orchestrator. That will be research plan dot sources. Research plan dot sources, because that's where we told it to keep our sources. Research plan dot sources. So we get that. And let me just complete this by saying research sources. So it will say orchestrator generated so number of research sources, which is good. Next, let us take a look at them. For I source in, let's enumerate that so that we can get our I. Enumerate. And I'm just going to copy this, which research plan sources. I want to start at 1. And here we can simply say print the number and the source, the position and the source. So this is good. We're printing out our sources so that we can see it when it is generated. We know that we're generating some sources there. And then we can also print the reasoning behind this. And I'm just going to go emoji again and say I want a light bulb here. Do I have a light? Okay. Light bulb. So we say our reasoning. And we'll just say research plan dot reasoning. Research plan dot reasoning. And here I'm just going to add an action point that says preparing to dispatch to nodes. Yeah, preparing to dispatch to nodes. So yeah, we're done with all the printing out just to make sure that we're getting stuff back from our orchestrator node. But the very important thing, the most important thing, is to make sure that we return our sources back into state. The sources that have been generated from this orchestrator node, let us pass it to state. So that will be research plan dot sources. Good. So that's our first node, our orchestrator node called plan research. It is going to break down our topic into different sources, and we can then start researching those sources. So let me jump out of this function. Then we can collapse it. And the next node we're going to be creating is our worker node. We're going to be creating our worker node next. Now, this worker node is going to take in a private state, but return back to the overall state. It's going to return its results back into the overall state. It will receive data in its private state, and it will return the result into the main state so that the reducer can add it to the aggregated results, and the orchestrator can decide what to do next with it, or the synthesizer node can then grab that final list of outputs and prepare a final report. So let us create our worker node. Say worker node, and I'm going to call that research worker. Research worker is going to take in the worker state, but it returns back into the overall state. That's good. First, let's get a worker ID. Worker ID from state. We're going to be passing in a worker ID. We're going to be generating worker IDs and passing it into this private state when we are spinning them up. So say worker ID, then source. The source will be what has been passed to it as the piece of the generated sources that it is to work on. So get those two. Let's add the print statement here. A worker node that is researching. That would be like let's do magnifying glass. Yeah. So say worker and specify its worker ID. Then we'll say we're searching and call the source. So as we're searching this source, let's put some quotes around here and say dot dot dot. Okay, so we get our worker node or our worker ID, we get our source. You will still see how we'll pass these two in when we're adding the edge, the conditional edge. Then we just say the phrase. Then we just add a print statement that shows that this is our worker of this worker ID and it is currently researching this particular source. Now let us bring the prompt that is going to instruct this worker node on what to do. There's also an elaborate prompt, so I'm just going to bring it in and we'll go through it. So here we paste in our prompt. Now let's read through. It says you are a specialized researcher investigating the research topic, the entire research topic. Your specific focus area is this source. Conduct thorough research on this aspect and provide 1. Key findings, 3 to 5 specific points. That's the most important discoveries or facts under this talking point. Data and statistics, relevant numbers, percentages, or quantitative information to back up the claims. Insights and analysis, sources and credibility, and implications. Why does this matter for understanding the overall topic? And you also see why it was important that we pass in the overall topic to this private state. It gives it more context on what the piece of that topic it is to research on. So it gives it context about the overall topic so that it knows how that subtopic fits into the big picture. So provide specific, or rather be specific, factual, and provide depth on this particular aspect. So that's good. It knows what to do. Let us fire this prompt into our LLM. Here we don't need to use the augmented LLM. The normal LLM is fine because we want to generate text for that section and not a structured output. So we'll say invoke prompt dot content. On the content, then we're going to create a findings dictionary because we want to return a dictionary as is defined in our state. Each worker returns a dictionary, and inside that dictionary we're going to have the worker's ID, set to worker ID, the source that was researched, and what we got back from our research. Good. Then we can just add a nice print statement here that shows that we're done. Like putting a check mark to that so that we know what it does. Yeah. So, by the way, feel free to ignore my emojis if you are not a fan. So, worker with this worker ID, I think I just copied that from here. Say worker with this worker ID is done. Say research complete. Search complete. That's put a new line there so that it doesn't affect any thing that comes after it. Now the most important thing we need to do from this worker node is that we need to return our worker findings back into state. We need to return it back into state. Now we got one finding. Let's say findings. We got one finding from this worker, and like I said, let's just go back up here. These worker findings from the overall state is where we want to aggregate all our findings from each worker. So they need to return back to that state. And like you can see, we made it a list of dictionaries and we gave it the add operator function as its reducer. So whenever we pass a new finding into this list, it will be appended to the list. So we scroll down and we say worker findings. We can simply pass in our findings into a list. So it should just add that. You just add that to what's already there, based on the sequence with which each node finishes its operation. So yeah, we have our findings being sent back into state, and we're done with our worker node. Now to create our final node, which is the node that is going to gather everything together. That's all the research done by each node and put it together into a final report. So here we say synthesizer. I'll call it, def synthesize report. Give it state, overall state, and it will also return overall state. So first, I'm just going to quickly add some print statements here to show that we are now in our synthesizer node. So print synthesizer. Let's take some notes. Yeah, this guy. So this will be the synthesizer. And to say combining insights from all workers. Combining insights from all workers. Then I'm just going to repeat this under. Don't worry, all this is going to be useful when we are visualizing. You don't want to be running things in the console and you don't know what exactly is happening when. So yeah, say print processing findings, processing findings from all the worker findings. So it will be states, worker findings. I'm just going to say research findings. Research sources. Yeah. So the findings are from the sources. So yeah. Now let us get all the findings all together. I'm going to say all findings. All findings equal. First, let's get double new line here. Let's put a delimiter, make it 70, and also add it to another double new line. Then we can say all findings plus equal a double new line once again, and we want to call the join function, pass it a list, and for each of the finding we want to say research area, search area. Now I'm going to have a loop, but let's put a loop down here. Let's put it down here so that it doesn't look like something just appeared from nowhere. So for f in state worker findings, yeah, good. So then we can say f worker ID, and f source. Put a new line after this, add some dashes, and then put the content on a new line. Okay, so yeah, we're going to loop over our worker findings. Then for each worker ID, researching the source, we create a new line, add some dashes, and we'll put the content for the findings. That's the content that we're returning here. We scroll down, you'll see it here, content. So for each of the findings, we want to just display what we found. So let us have that there on display. So that will just display what we got from each finding. But then let us instruct what the synthesizer is actually going to do. So I'm going to grab the prompt for that and get back. Let's paste that here. And now let's go through this prompt. It says you're synthesizing a comprehensive research report on this research topic. You have received detailed findings from the worker findings. Specialized researchers, each investigating a different aspect of this topic. So we give it all the findings, all the research findings that we built up here. All the research findings we built up here, we give it to it. So it then says create a cohesive, well-structured research report, 500 to 700 words, with each of the following sections. Executive summary, that's provide a high-level overview of each takeaways. Then introduction, the context and importance of this topic, the scope of this research. Then the key findings. So you take all the findings and you integrate insights from all of the research areas, organize them thematically rather than by source. So let them flow in the right order. Then use specific data and examples, which you can also get from the information that they returned. Then analysis and synthesis, identify patterns across each research areas, highlight connections and relationships, and note any contradictions or tensions. Then talk about the implications and finalize with some main takeaways and areas for further research. Then some important instructions to wrap up. Write these as a unified flowing report, not as separate sections from each researcher. So don't just do what some people call cut and join. Make it flow. You are not to use the content as is. Actually, just feed from the content and use it to build a proper article from top to bottom. Then integrate findings naturally across teams. Use specific examples and data from the research and make it professional and authoritative. So, good. Very well detailed prompt. Now let us process our prompt. This is going to be our final report. Say final report equals LLM.invoke our prompt, and we can get our content from that. That's good. Let's also indicate that our synthesizer is done. Come here. This turned out to be a very long example, but like I said, real world examples, that's what we want to see here. Makes it more fun and make you understand where these strategies are actually needed. So synthesizer, say final report complete. And we can simply return that final report back into state. So final report. Awesome. Now we're finally done with our nodes and we are at line 188. So yeah, we have our orchestrator, our worker node, and our synthesizer. Now we need to take what we get from our orchestrator node and dynamically spin up worker nodes. We need to do that, and that will be done using a conditional edge. We're going to use a conditional edge that will spin up a bunch of send commands, and each send command is going to take a piece of the data, that's a source, worker ID, and the research topic itself, and pass it to a worker node. It's going to pass each of them to a worker node. So let us build that up. Let's write the function that is going to perform the conditional edge. So I'm just going to say conditional edge function, and that will be create research workers. Create research workers is going to take in the overall state. And here, let us know that this is where we are. I'm going to put this road sign emoji, and I'm going to say dispatcher, say creating research workers dynamically. Good. And we're going to then spin them up. So to spin them up, we're going to be returning a series of send commands. That's how you spin them up dynamically. Like I said, if you still don't know how send works, do well to check the send lesson in the LangGraph fundamentals. So we need to return a list of send commands, and we'll say for I source in rate, and here we get our sources. So from our sources, not courses, our sources, we loop through over our sources here, and for each of the source, we want it to send to a research worker node. To a research worker node, and what do we want to send? We want to send this piece of data. First is the source itself. So send the sources to research. We also want a worker ID, which you can generate with any strategy you want, but for now I'm just going to be using the iterator count. And also we want to send the research topic for context. So it's a research topic. And we want to send research topic, which we'll get from the state. So research topic. So loop through our sources, and for each of them, use this send command to spin up a new research worker node and give it this piece of data that goes into its private state. Yeah, so that's everything. That's everything for our conditional edge. And now we can build our flow. We can build our flow and our entire graph. So let's start that. Let me say build graph. So first, I'm going to say builder equals state graph. And here we'll pass overall states. Our state schema. Next, let us add our nodes. So I'm just going to say builder.add node. And the first node we're going to add is our orchestrator. We're going to name it orchestrator. And this is going to be set to our plan research function. Then we add our next node, which is the research worker. And we'll set that to our research worker function. Then we add another node. That will be for our synthesizer. We'll call it synthesizer. And that will be our synthesize report function. So we added our 3 nodes. Now let us build the flow. Let's build the flow. So for our edges, we say builder.add edge. And we want to go from the start node to the orchestrator. Start node to the orchestrator. Then from the orchestrator, we then go to all our worker nodes. So we need to add a conditional edge. Say .add conditional edges. And for that, we want to go from orchestrator. And then we pass it this function. Pass this function that is going to go to worker nodes. And for each of them, just go to research worker. Even though send is going to do that, but let's just have it here. So this is good. Then finally, let us go from all the research workers. Go from all the research workers. I'm just copying that from here. Go from all the research workers to the synthesizer. And once we are done synthesizing and building our final report, we can terminate the graph. That's awesome. That's awesome. Now let us compile this graph and use it. Let's compile the graph and use it. So I'm going to say builder, nope, or graph rather. Graph equals builder.compile. which is good. Now to test our graph, I'm going to be bringing two topics. We're going to be bringing two topics, and you can play around with each topic. I'm going to be running one of them, or I might just run two of them, but I'm going to bring in two topics that we're going to use to test out this. So let me just grab that. So I'll paste those in. And here we have a healthcare topic that says the impact of artificial intelligence on healthcare delivery and patient outcomes. And we have an environmental topic that says renewable energy adoption barriers in developing countries. So you can use any of these topics to play around, and you can also create your own topics. So yeah, I'm going to take a topic variable which we're going to be alternating for any of our topics. So I'll start with the healthcare topic. And here you can run our graph. Let me start with my borders again. Middle here we can print our topic, and say topic. Okay, so then we can run our graph. So result equals graph dot invoke, and we can pass it our initial state. For our research topic, we just say topic. Our sources, we'll start with none. We're starting with 0 sources, so there's no initial sources we're passing. Everything comes from the orchestrator. Then our worker findings will also be set to an empty list. It's good. Now we can come down here and print our result. I'm going to copy this because I'm doing something similar down here. Now here we'll say final synthesized result. And then print our output. That'll be result, final result, or final report. I think it was final report. Final report. So we get our final report from our state. That's here. Final report from our state, and print it out. So yeah, that was a lot, but it's all to clearly show how this workflow is implemented. And now we can run it. Now make sure that you have your API key in place. So ensure that you have your API key in place. Also make sure that you're in your virtual environment. Sometimes you can make that mistake and just want to run your code without activating your virtual environment. And now we can say Python O2 workflows O2 12 Orchestrator-Worker.py. Now we typed a lot of stuff and there might be some errors, but let's just hope we don't have any errors. If there's any error, we'll fix it anyway, but let us just run the code and see what we get. So yeah, our topic, the orchestrator is planning the research strategy, so it's generating its sources. So get an error here, says worker ID. It can't find worker ID here in state. That should be inside our research worker node, so it can't find the worker ID. Let's go up, see if there are any errors too. So it was already dispatching here, so yeah. So let us test that because it's already giving us some results here. Let's close this. Let's see what we got wrong. So research worker, state worker ID, the source. Let's go down to where we are dispatching to see whether we gave it the right worker ID. Oh yeah, that's where the error came from. So we go to worker here instead of worker ID. Sorry about that. That's my mistake. So worker ID. Let's close this. Pull up the command line and let us run once again. Like I said, we did type a lot of stuff, so yeah, there might be a couple of errors. So planning again. Generating sources. And now we can see the workers, we can see the output of each workers, worker 1, worker 2, worker 3, worker 4, worker 5, because we're actually spinning up 5 of them because we told our LLM to give us 5 sources. So now it should be going to the synthesizer node so that it generates our final topic. Oh, the workers are actually just completing. So, and they're completing out of order, as you can see. Race conditions. Completing out of order. Number 1 finished first. Number 2 second, then 4, then 3, then 5. Then synthesizer is combining insights from all the workers, processing the findings from all the research sources, and in no time we should be getting our final report. And yeah, we get our final report in Markdown. The final report, when we scroll up, we have our executive summary. Artificial intelligence is becoming a transformative force in healthcare delivery and patient outcomes, blah, 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 blah. Our introduction, the key findings, where it actually makes use of what we got. Did analysis and synthesis, implications, and then conclusions. Very specific on how many words that we want, whether we wanted it to be a 1,000-word article or a 5,000-word article or a 5,000-word report or everything. But those are things you can also specify so that you can know how elaborate it should be. But this is quite compact and it follows exactly what we want it to do. We see our let's scroll up a little bit from the very beginning. So we can see our topic. The orchestrator started planning. It then generated 5 talking points. And it gave us the reasoning behind it. These sources were chosen to provide a holistic view of AI's impact on healthcare, and it gave more details why each of them was chosen. Then our dispatcher dispatched to the nodes dynamically. Then worker 1, worker 3, worker 2. You can see it's even out of order because it's not doing it sequentially, it's doing it at the same time, simultaneously. Then it also started completing its research. 1, 2, 4, 3, 5. Then the synthesizer took everything from all the workers, synthesized it into a final report, and now we get our final synthesized result. How awesome is that? That is how you use the Orchestrator-Worker Workflow. So, you've often heard of the term LLM as a judge. Let's put that somewhere here. LLM as a judge. Yeah, this is where an LLM produces an output, then you use another supervisor LLM to actually check the work of the first LLM to see if it is up to a particular standard or meets a certain criteria. That's what LLM as a judge is all about. One LLM is doing the work, another LLM is supervising and making recommendations until a satisfactory criteria is met. The Evaluator-Optimizer Workflow helps you to set up this type of system. So imagine that you want to generate a report. So you generate a report and you use an LLM. You use an LLM to generate a particular report. Now you then have another node in your graph that has been given a set of instructions, criteria, like a checklist, to check the work of this first guy. So this first guy generates his output and sends it to this guy. This first guy is called the generator/optimizer. Optimizer. Good. So this first guy is called the generator/optimizer. And this guy is called the evaluator. So the generator generates a first draft, sends it to the evaluator. The evaluator then checks this draft against its list of criteria or checklist of standards to be met, scores the work, checks if the score is above a certain threshold. That's one of the main metrics that you can use to determine whether it is good enough. If it is not at that threshold or above that threshold, it will be sent back. It will be sent back. Now, it won't just be sent back. It will be sent back with a list of recommendations. Yeah, correct this, fix this, clean this up, remove this. To send it back, then the optimizer is going to optimize. So this node performs 2 functions. When it is producing the first draft, it is serving as a generator. Then when it is correcting its draft based on the recommendations from the evaluator, it is serving as an optimizer. So it generates a draft, sends it to the evaluator checks it, sees if it is good enough. If it's not good enough, it sends it back. If it's not good enough, it sends it back. This guy will fix again, send it, he will check, send it back, and if it is actually producing the right instructions on how to correct the document, it shouldn't take too many iterations for this guy to generate a satisfactory draft. The evaluator will see it and approve it, and then your workflow can continue. With the next steps. So yeah, that is how this pattern works. It's an iterative workflow where one LLM call generates the content, that is the generator or optimizer, and another LLM evaluates the content, that is the evaluator. If the evaluator determines that the content doesn't meet the success criteria, feedback is going to be provided and sent to the optimizer to create a revised version. And this loop is going to continue on and on and on until both, or rather the evaluator agrees that the criteria is met, or you set a total number of iterations like 5. Yeah, don't go beyond 5 iterations. After 5 iterations, just approve the work. We don't want this loop going on and on and on and on and creating so much latency in this process. So after like 5 iterations or 3 iterations or 6 iterations, just be done, just mark it as okay, and we're good enough with that amount of corrections. So that is how this works. That's how it basically works. Now, getting into the technical implementation, to determine whether the draft is good enough, it needs to use a decision step. It needs to have a decision step where it checks, does it meet the criteria? If it meets the criteria, it will simply pass it to the next node. And if it doesn't meet the criteria, it's going to send it back to the generator or optimizer, depending on whatever state the workflow is in. And this is done with a conditional edge. This is done with a conditional edge. Also, you have to make sure that a measurable standard is set within the evaluator so that it can properly determine when the draft is good enough. Like I've mentioned earlier, this can be an accuracy score. You can say anything above 8/10 is okay. Anything below that is not accepted. It can also be a checklist. It should contain this, it should contain that, it should contain this, it should contain that. And it will check through all the items in that checklist to see if the draft satisfies the requirements in the checklist. It can also be a quality threshold. It can be a quality threshold. Just make sure that you're setting something that is measurable so that this loop doesn't continue to go over and over and over and just spin itself into an infinite state. Now, what use cases can you put this workflow into? We're going to discuss 2 major ones. First is in a legal document review. In a legal document review. So you can generate a contract clause and you evaluate the contract clause for completeness, clarity, and risk factors. Then, based on legal concerns, you continue to refine until that contract is legally sound. So that's one thing you can do using this workflow. Another thing you can do is use it for code generation. You can generate a solution to a problem. You can evaluate that solution for correctness, for efficiency, for compliance with your style guide. You can also check it for bugs. You can check it for bugs or if it violates any type of business rules that you have set internally. And you continue to iterate all these checks on the code that is generated until it fits all these criteria. So those are 2 use cases that you can put this to, but I'm sure in your mind now you're already thinking of a bunch of use cases that this can perfectly fit into. And we're going to be demonstrating one of those use cases next. In this video, we're going to be using the Evaluator-Optimizer workflow that we just learned about to build something helpful for an e-commerce system. We're going to be building a product marketing model for an e-commerce system, a product marketing workflow that generates a compelling product detail for a product. It generates compelling product details for a product. It will take in the name of the product, its features and target audience, and it will build details for a compelling product page. It will build compelling details for a product page, an elaborate product page. Then this generation is going to be done by the creator or the generator optimizer node, and we will have an evaluator node that judges the output. Let me start creating the file as I'm talking so that you will know that, yeah, your screen is not frozen. So it would use an LLM to generate, and it will use another LLM to judge what has been generated. That's the product detail that has been generated. And to make things unbiased, we're going to be using an OpenAI model for the generation and optimization, and we're going to be using a Gemini model for the evaluator. So Gemini will get to judge OpenAI. That's what we're going to do. So we don't have OpenAI judging OpenAI, even though you can still have setups like that. You can have a smaller OpenAI model being judged by a bigger thinking OpenAI model. But just to keep things on separate platforms, we're going to be generating with OpenAI, and we're going to be evaluating with Gemini. You can also use this to improve a lot of small language models. By the way, we need to install Gemini, but we'll do that soon. You can also use it to improve the work of small language models. So you can use SLMs to generate and use an LLM to evaluate. So it will just train the SLM to generate better outputs just by listening to recommendations from the larger model. So first, let us get Gemini in. We've not installed Gemini here. That's the LangChain Gemini wrapper. So let us get it in by saying pip install LangChain Google Gen AI. Make sure you're in your virtual environment, and in no time that should be done. Good. Another thing you want to make sure is that you have your key, you have your Google key in your environment. So you want to do export Google API key and set it to whatever the value of your Google API key is. That's your Gemini API key. So make sure that those are done, and then we can begin. So first, let us get our imports in, starting with the OpenAI package. At OpenAI. Then let's also get Google in. LangChain Google Gen AI. And for that, we import chat Google Generative AI. Good. Next, let us get our graphing tools. And after that, let's get some stuff from the typing library. Import type detect, list, and literal. And because we need structured outputs, because our evaluator needs to produce our generator needs to produce structured output for our evaluator to be able to know what to evaluate. We'll need to get Pydantic here so that we can generate a schema for our structured outputs. Base model and field. That's good. Next, let us define our state. Let's define our state. So we'll call it optimization state. Pass it Pydantic's base model. And what do we want here? Now we want to supply as much details about the product as we can, because the more details we can supply, the more the LLM can generate a comprehensive product page. So first, let's say product name. That'll be a string, which is the name of the product itself. Product features. Product features is going to be a list of strings. Then we have target audience. That is one important thing for a product marketer to know. to generate something appropriate. I was privileged to work in a product marketing department as a technical writer before, so it was really, really fun seeing the magic they do with words. So yeah, current description, that is the current generated product details, what was generated. Then we need an evaluation result. That will be a dictionary. So this is what the optimizer or generator is going to produce. It will always be the current description. Anytime in state, it will be the current description. Then the evaluator is going to produce the evaluation result. So get the evaluation result, which is a breakdown of the evaluation. Then we will also have a feedback. We also have a feedback. This might not be necessary in some cases, but this is just to kind of like summarize everything from the evaluation results, because the evaluation results might say like 5 different things, which definitely the optimizer is going to take into account, but it's also good to just get a summary so that you just see how everything kind of connects together. The more information you give to an LLM, the better it can perform. So then we also have iteration count, just to monitor how many times we've looped over. Iteration count is going to be an int. Then we have max iterations, which is also going to be an int, so that we know when to check out. Then we need a boolean to know when we are approved, so we'll say is approved. And we'll just store the iteration history also somewhere so that we can see the versions, the different versions that were produced throughout the correction process. So that will just be a list of dict. The evaluation results is a dict, so this will just be a list of dicts. So yeah, all the evaluations made in order so that we can see everything that was. Alright, this is not for the versions actually, this is for everything that was suggested at each time, at each point, everything that was returned from these evaluation results. So we know what was recommended and why we have what we have now. So that's good. Now we need to write schemas for our structured outputs. We need to write schemas for our structured outputs. First, we need one for our generator optimizer node. This is for it to provide a defined output that the evaluator can take and evaluate. Then we also have to provide another one that the evaluator is going to generate for the optimizer to be able to optimize the generated details based on the observations that the evaluator has made. So we need two schemas for structured outputs. One structured output for the generator, one structured output for the evaluator. So let's create the first one for the generator or optimizer. Say product description. Let's give it a Pydantic based model. Then the first thing we want is an headline. We're going to generate an headline. These are the things that we want the optimizer or generator to generate. First generate an headline, a catchy headline. So we'll say description. Description for that is like we said, a catchy headline. And we want it to be like maximum of 10 words. Yeah, so don't start writing phrases or long sentences. So then we have description. Description 2 is going to be a string. And we want it to be, let me copy this description here. Want to be the main product description. $100 to 500. 500? No, 500 is too much. 100 to 150 words is okay. Words. So 100 to 150 words. Another thing we wanted to talk about is key benefits. So anything you just want the product marketer to highlight on the product, you add it here. So we want to talk about the key benefits of the product. For this, description is going to be 3 to 5 key benefits as bullet points. bullet. Then we also want to have a call to action. Yeah. What is marketing without a call to action? So also want to have a call to action. A string. And description of this will be a compelling. Now I need quotes there. Compelling call to action. Compelling call to action. So yeah, we want a headline for our product. We want a description. We want the key benefits. And we want a call to action. If you are describing an electronic product, you might want to put features, like what are the features, what are the specs for that particular product. So just build that schema according to the needs of your application. Now let us build out the evaluation schema. So evaluation. Base model. And what do we want for evaluation? First, we want an overall score. An overall score is an integer. The field description, maybe overall quality score rather, between 1 to 10. Between 1 to 10. We're also going to use Pydantic to set that, say greater than or equal to 1, and also less than or equal to 10. Now, we still have a bunch of stuff that we're going to bring here. I think we're going to be defining like 6 of them. So let me just bring them in and we're going to explain them so that you don't have to watch me type everything. So copied and paste. So after our overall score, we also want a clarity score. Clarity score is also between 1 to 10. Persuasiveness score, 1 to 10 also. Audience fit score, target audience fit, is approved. That's a Boolean. And it should be set whether the description meets standard that are greater than or equal to 8. So 8 is our threshold. Between 1 and 10 of our overall score, we approve when it is equal to or greater than 8. Then strengths, what works well in this particular draft. Weaknesses, what needs improvement in the draft. And specific feedback, a detailed actionable feedback for revision. So that's our evaluation model. Now we have the type of output that is going to be generated from our Generator-Optimizer node and the type of output that our evaluator node is going to produce, each with properties that help us to specifically determine how well we are doing. So next, let us define our LLMs. Let's say LLM. The first LLM is going to be for OpenAI. So say chat OpenAI. The model is going to be GPT-4o mini. Now, be careful with the type of models you use because we're augmenting them. We're augmenting them with structured outputs. And GPT-4 doesn't support structured outputs. So you can have, it supports JSON parsing, but it doesn't support structured outputs. So if you use GPT-4, it's going to blow up in your face. So just make sure that you check the docs of your provider to make sure that the model you're using supports structured output. Same with when you're trying to use SLMs or local models. You want to make sure that you're using an SLM or a local model that supports structured outputs. So these are OpenAI LLM. Next, our Gemini LLM. And for Gemini, we're going to call chat Google Generative AI. And the model we're going to use is Gemini 2.5 Flash. Or let's use the light version. There seems to be some new tight quotas on Gemini 2.5 Flash now for the free plan. So, but the light works good. So yeah, we have these two in place. The next thing we're going to do is to write the nodes. We need to write the nodes for our Generator-Optimizer, that's one node, Generator-Optimizer node, and our Evaluator node. So in our Generator-Optimizer node, we'll first check if we are performing the action for the first time. If so, we'll simply generate the first draft. If we if our iteration count is greater than 1, meaning that this is not the first time we're performing this operation, then it means that we want to optimize based on the evaluator's recommendations. So we're going to perform those two based on the condition or based on the state of the workflow. So let's define our optimizer node. Put a comment here and say optimizer generator or generator optimizer, whichever one you choose to call it. Some people also call it creator optimizer. Just call it the one that makes you understand it best. So yeah, let us say generate description. That'll be the name of our function for this node. It's going to use and return our optimization state. So optimization state. Now down here, the first thing we want to do is get our iteration. Say iteration equals state, and we get the iteration count. Then I'm going to put some print statements here quickly. Say new line. Then we have have this here, and also a version of it down here, just without the new line. And in between that, say print. You need an F string here. This is going to be the optimizer. I'm going to give it a nice writing emoji here. Say right. So optimizer. And let us also display the iteration so we know which iteration we are on. Iteration, good. Now we need to get our LLM ready to perform this operation. And it needs to generate a structured output, so we need to augment it. So say optimizer LLM. And that will be LLM dot with structured output. And we pass it our schema for the structured output it is expected to produce. That will be the product description. So pass the product description down here. Good. There's a red line somewhere. Okay, yeah. You'll notice that the file name was red. So product description. Then let us check if we are on our first iteration. So if iteration equals 1, that's if we are performing this for the first time, that means we are trying to generate a new draft, the very first draft. We're trying to generate the very first draft. So we're going to print and say creating initial product description. And here we need a prompt that would help us instruct the model to create a first draft. So I'm just going to grab that from the GitHub repo that you also have access to and paste it here. So we have that in, and the prompt says create a compelling product description for this product. We get the product name from state, we get the features, we loop over them, or rather we create a comma separated version of them so that it can be serialized into here. Then we get a target audience, and the requirements are headline should be catchy and concise, maximum of 10 words. We already mentioned that with Pydantic. Description should be engaging and informative, key benefits, and call to action. So make it persuasive and tailored to the target audience. Good. So this will be our prompt if we're creating this for the first time. However, if we have been here before, then first we're going to print and say, let's see an F string there. We'll say refining description based on evaluation feedback. I don't think I need an F string here, actually. It's fine. Okay. So then we need to have a prompt for refinement. This is the prompt for generating the very first draft. Let us bring in our refinement prompt. Good. So here, this prompt says, improve this product description based on feedback. We'll give you the product name, we'll give you the target audience, we'll give you the current description. That's the one that we are working with right now. Then we go to the evaluation scores. The overall score is this over 10. Clarity score, persuasiveness score, and audience fit score. So we give it all the scores, the current scores, and we tell it that this is the summary of the feedback. This is summary feedback, and we give it some instructions that we mark as critical. It says focus on the specific weaknesses mentioned, make targeted improvements to 1, address each point in the feedback, maintain the instructions that we're working so that you don't break what is already working. Then increase scores in weak areas, generate an improved version that addresses all feedback. So you have to address all the feedback so that we can get as high as a score as we want and move on. So we have the prompts. Now we can jump out of this loop and then generate our description. So we get the Optimizer LLM. Let's grab it up here. Let me collapse this. So grab our Optimizer LLM. We then invoke it with our prompt. Work with our prompt. Then we're going to create a formatted display. We're going to take the structured output and create a textual version of that we can then store as our current description. So let's say formatted description. This is so that the evaluator can once again receive what we got as a textual draft and then give us an evaluation based on that. So I'll create a multi-line string. First, we want an headline, not deadline, headline. An headline that says description dot headline. Description dot headline. Then we also want the description itself. And the description will simply be description dot description. Then for key benefits, we'll just loop over that. I'm going to say for benefits in description dot key benefits, which is where we stored the benefits. Description dot key benefits, we want you to print each benefit as a bullet point. So benefit, each benefit as a bullet point. Then put everything here into a list. I put everything here into a list. Then take this list and join each of them with a new line. Character 10 dot join. Join each of them with a new line. Then our call to action. For our call to action, let us have description dot call to action. Description dot call to action. So that should be our formatted description, and it's going to be the current description that the evaluator is going to look at and evaluate. So that's all good. We can print out our description here. We can say print generated description so that we see each output that is coming out. And here we can just put a line here. And then below that we can print our formatted description. And add a new line after that. Now, most importantly, from this node, we need to return our current description. Our current description, which is going to be this formatted description. And we need to increment our iteration count. So iteration count will be the current value of our iteration plus 1. So that's good. This is our generator node, our optimizer generator node. It is performing the work of generating in this if block and optimizing in this else block. And whichever way is going to generate this product description, and we will save it in our current description. So let's just collapse this. And after that, we can move to our next node. Now, our next node is the evaluator node. Now, this node will always take the formatted description. That's the current description from our optimizer node. And it is going to evaluate it. It is going to score it. It's going to approve or deny it. And if it is denying it, it's going to make optimization suggestions that the optimizer node can pick up and then use to refine the draft. So let us create the evaluator node. So call this evaluate description. The description can take state to also take our optimization state and return it. Then in here, I'm just going to copy this and put it here. We're going to have that glass here, that magnifying glass here, to show that we are investigating. And this is going to be the evaluator. And it's simply going to say reviewing description. So this is good. Now for it to review, we need to augment the LLM so that I can use that to create the structured output of its review. So I'm just going to say Evaluator LLM, and that will be equal to our Gemini LLM because we're using Gemini to appraise OpenAI. We'll say with structured output, and we will simply pass our evaluation schema here. This is good to go. And the next thing we're going to do is write out the prompt that is going to perform our evaluation. So I'm just going to bring that in and we can study it and continue. So let's paste that here and read through. It says evaluate this product description objectively. We give it the product name, we give it the target audience, we give it the description that it is to evaluate, which is our current description. And we say evaluate it on this criteria on a scale of 1 to 10, which is the scale we gave all our scores. Clarity, is it clear and easy to understand? Persuasiveness, does it effectively sell the product? Because that's basically your job as a product marketer. Audience fit, does it resonate with the target audience? Now the approval criteria, the overall score must be 8 or higher to approve. Provide scores for each criterion. Overall score, that's average of the criteria. Then whether it's approved. Specific strengths, what's working well, specific weaknesses, and actionable feedback for the next iteration. And it says be objective and constructive, so don't be biased. So that's good. Now we can say evaluation and get that by calling our evaluator LLM, which is our augmented Gemini LLM, and tell it to invoke the prompt. Invoke the prompt, and we're going to be printing out a bunch of stuff from our evaluation scores. So first say print evaluation results. Let's put a border under that. Then we'll print our scores. First, let us print our overall score. That will be evaluation dot overall score, and that will be set over 10. That's good. Now I'm going to copy this a few times. Let's see, 3 more times. so that I can use it to do our clarity score. Clarity is going to be clarity score. Then next is going to be our persuasiveness. And that will be the persuasiveness score. Persuasiveness. Yeah. That'll be our persuasiveness score. And the last score will be audience fit. Audience fit, and that will be our audience fit score. Okay, all over 10. So we have our scores printed. Then we need to print our status. And that will be set to approved. Let's put a check mark here. So it will be approved if our evaluation dot is approved property, as we define our structured output, if it is true. Else we're going to be printing that, yeah, we need some work here. We have an X, yeah. So we're going to be printing needs revision. Needs revision. So we're going to print approved if the evaluation is approved, else it needs revision. Then let us print some strengths. So print strengths. And for strength, we'll just loop over our evaluation dot strengths list. Say evaluation dot strengths and for this we're simply just going to print the strength, a dash, and say strength. Okay, let's do the same thing for weaknesses. I'm just going to copy this, come down here. Let's get this print statement for weaknesses too. Weaknesses, so we have weaknesses or weakness, and we'll take it from evaluation.weaknesses, and we print each weakness. Okay, I think I'm using a new line here, okay, for weaknesses. So strengths and weaknesses. And finally, let's also print the main feedback. What feedback did we get? So feedback, that will be evaluation dot specific feedback. Is that what we called it? Specific feedback. Let's see. Evaluation. Yeah, specific feedback. So evaluation dot specific feedback. That's fine. And after that, we're going to build an iteration record that we can store in our iteration history. We're just going to build a dictionary that we can store in history. So I'm going to say iteration record equals and iteration will be state iteration count. And just to save some time, I'm just going to paste the rest in. Good. So we have our description, we have our scores, the overall score, the clarity score, the persuasiveness score, and the audience fit. If it's approved, and our specific feedback. So we'll just get this, and we can say history equals state.get, get our iteration history. If not, just pass us an empty list. Then we can take this new iteration record and append it to our history. Iteration record, append. And now finally from here, let us return stuff to state. We have a bunch of stuff we need to return to state. So first, our evaluation results, evaluation result. We'll just say evaluation dot model dump. Then for feedback, that will be evaluation dot specific feedback. I think that is here. For is approved, that will be evaluation is approved, that I can get from here. And for iteration history, we can simply just pass in our history. So yeah, this is our evaluator node. This is our evaluator node, and we're done. We're done with the evaluation node. Quite a node. So we have those in place. Now we need to determine how we're going to check our success criteria and see if the evaluator approves the draft or not. Then take the appropriate action based on whatever the result of that is. And as you may have guessed, we'll be doing this using a conditional edge. If the evaluator approves the draft, then we end the node. If not, we're going to route back to the optimizer that is going to refine the draft using the evaluator's observations. So let us create the edge function that is going to determine that. So we call it decision function. And we'll call this should continue. Should continue. So states, optimization states. Now this is going to be returning a literal that would say optimizer or end. So if it returns optimizer, it is telling us, yeah, we need to refine. If it returns end, it's telling us that we need to terminate the node. So let us write that logic. We'll say if state is approved, if the draft was approved, the draft was approved, then we're going to print success. We get a new line and just say success. No edit. I'm going to say success. Description approved. Let's give description a capital. So description approved, exclamation. Then we just return end, so that it knows that it's to go to the end node. Also, if we notice that the number of iterations, we notice that the number of iterations is already greater than what we said will be the maximum. If it's greater than what we said will be the maximum, then we might want to check out too. So I'm just going to copy this, put it here, and here I'm just going to put a warning emoji that's going to tell us, yeah, you kind of exceeded your limit. So here we'll say max iterations reached. Then here we can put a message that says stopping at iteration. Now say states. Or do we have an F? Oh, we don't have. We need an F string here. Okay. State iteration count. Or we stopped at the previous one, so we'll say -1. State iteration count -1. Because we're on a current iteration, but we can't proceed, so we need to say that we stopped at the previous one. So we also return end. So just terminate the node, we're good. Now, if all these don't happen, then simply print that we're continuing. So we'll say continuing, say routing back to optimizer for iteration. For iteration state, okay, F is missing. State iteration count. So we're going back for that iteration and simply is back. Simply return optimizer. Return optimizer. So in these two cases, if it's approved, end the node or graph. If it is, or rather, if it has its maximum iterations, end the graph. Else, return back to the optimizer to refine the draft. So this is good. We have our edge function in place that is going to be making our routing decisions. Now we can start building the graph. So say build the graph. And for that, we'll say builder equals state graph. Pass it the optimization state. Then we can start adding our nodes. We have just 2 nodes. So add node. Our first node is the optimizer. And that will be done by the generate description function. Second node is the evaluator. And our evaluate description node is going to do that for us. Then we can start building our flow. So to start that, we'll say builder.add edge, add edge. We start and go to our optimizer node. Then from our optimizer node, we go to our edge node to give ourselves the first score. Then we can then add our conditional edge from our evaluator node to determine whether we are going to terminate the graph or we are going to have to refine it through the optimizer. So we go from our evaluator, we ask, should we continue? And then we give it a mapping dictionary. So if it returns optimizer, then we need to go to the optimizer node. If it returns end, then we need to go to the end node. That's good. Either way, it is going to be terminated, so we don't need to add a specific node that directly goes to the end node. Somehow we'll find ourselves back at the end node. Now let's test this graph. First let's compile it. Say graph builder.compile. Then I'm going to be writing my first example for a fitness tracker. So I'll get some print statements in that just says evaluator optimizer pattern, product description, then example fitness tracker. Then let us actually run our graph. So result equals graph.invoke. Let's pass in some details for our fitness tracker. So first is product name. And for that, we'll say Fit Pulse Pro smartwatch. By the way, you can use any example you want. You can use any product you want, just to make it fun. For product features, I'm going to give you the list. I'll be pasting in some features in here. So heart rate monitoring, GPS tracking, sleep analysis, waterproof to 5M, that's 5 meters. 7-day battery life, smartphone notifications. Now let's look at target audience. And that's going to be health conscious professionals. Health conscious professionals, age 25 to 45. Then for some other defaults, I'll just bring them in. Current description is going to be an empty string because we will expect it to start from the LLM, the generation step. Evaluation results is just an empty dictionary. Feedback is empty string. Iteration count is 1, so that we know that that is the first time we're starting, and that is the check we're doing in the optimizer node. If iteration count is equal to 1, then we want to generate first, else we refine. Then max iterations 5, we want to keep it at 5. Is approved, definitely we'll start at false. Then the iteration history, where we just keep like a log of what has been recommended to be fixed. So after this test, we can then print our final output. I'm going to put a new line. So let me just do this. Say F new line and say multiply by 70 and duplicate this down here without the new line. And here I can say print final approved description, and down here we can simply print that final approved description, which will be our current description at that point. Current description. Oof, that has been quite some coding. So let's save this and hope that we got all our code right. There are no red squiggly lines, but that doesn't mean that we have not mistyped something. But let's run this. Let's run this and see what we get. So now we're going to be running the O214 file. So we'll say Python O2 workflows O214. Now remember, you need to have both your OpenAI key and your Gemini key in place. Basically, you have to have the keys for the LLMs you are using. So if you're just using 2 different OpenAI LLMs, just have your OpenAI API key in place. If you're using local models or anything, just make sure that your credentials are in the environment so that you can run this example. Let's put this up a little bit so I can get a full view. And let us run the Evaluator-Optimizer example. And we get an error. It says during the optimizer task, we notice that the optimization state object is not subscribable. Okay, what happened there? Let's check our optimizer task. First, let us see if we have any errors up here. Okay, nothing. Okay, let us check our optimizer task. Let's see what we got wrong. That's optimizer, yeah. State iteration count. Oh, this is interesting. I gave my optimization state base model instead of type dict. Yeah, like I said, even though we're not having any squiggly lines, that doesn't mean we have not created an error. So I gave it base model instead of type dict, so it was trying to look at it like an object instead of just seeing it as a dictionary. So yeah, sorry about that. Let us clear this. Scroll up, and now we should have creating initial product description. Let's go. Okay, it's drafting something there, and I think we have our final output. Okay, let's go to the top to see how it takes it from the top. So evaluator, optimizer pattern, product description, fitness tracker. So the first iteration, it created it and it generated it. and give us an headline: elevate your fitness journey with FitPulse Pro. Interesting. Description, forgive the formatting, it can be weird based on our white spaces. Description: discover the FitPulse Pro smartwatch, your ultimate health companion designed for health conscious, blah 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 blah. The key benefits, it generated some key benefits here and all that. Now that's the first draft, but let us see what the evaluation did. Gemini evaluated it to have an overall score of 8, just 8, just at the very tip of our score. So clarity was 9, persuasiveness was 8, and it was 8. Our strengths are appearing weird and our weaknesses are appearing weird. That's something we need to fix too. So, but yeah, you see, we get the feedback, but because it's 8, it approved it, and it told us that that is the final draft. Let's correct whatever is happening with the fitness and stuff. I saw that the syntax highlighting was a bit off, but I just felt maybe it was my team that was getting something weird. Let's see, where was that done? The evaluation should be in evaluation. Strength. Okay, so we are missing the F's. Yeah, we're missing the F's. So let's save that. Now let's try again. Let's see if OpenAI is going to fail this test at least, so that we can do 2 iterations, because it passed this one at first try. These are actually 2 powerful models, so it will most likely get something good. But like we saw with this previous example, it was just at 8. So yeah, that was just on the edge. I think it passed our first draft again. Let us see the score it got now. Oh, it still got 8. Still got 8. Interesting. Persuasiveness was 7 this time. Still got 8, so it still passed. Let's try again just to see if it would slip up one time. We just need you to slip up one time, please. OpenAI, just slip up one time. Just slip up. I can't use GPT-4 because it won't support structured output. It's not slipping up. It's not slipping up. It's still getting some good scores there. But anyway, yeah, that's what we wanted to do, and it's doing it. You might try some smaller models or some like local models that are like, let's say, a few parameters, like 12 billion parameters, and see and use them as the optimizer and generator. Most likely they will not pass it at first try. But yeah, with this example, we've been able to see how the Evaluator-Optimizer Workflow works.